Welcome to the introductory episode of this tutorial series. Hello, I'm Lily, a programmer when it comes to programming. The pre-existing image in some people's minds contains these keywords: difficult, abstract, brain-burning. Because of that, some people really want to learn this skill, yet hesitate to take the first step. As someone who has been coding for many years, I wanted to show people with zero programming experience that it's actually far less scary than it seems. So I made my first video, What is Programming? A 3-minute explanation showing that programming should feel simple, intuitive, and aligned with common sense. As a creator whose fans and hair volume are equally scarce, I hesitated. A structured tutorial requires far more work than a 3-minute video, and there are already tons of paid and free programming courses out there. But some self-learners told me that many tutorials either become impossible to understand after a few days, or are too long and detailed to stay motivated, leaving them stuck at the beginner's barrier. After studying many tutorials, I felt there was room to make something different. With these two features, first, more examples and visual elements to aid understanding. Sometimes we struggle not because the knowledge is inherently hard, but because it doesn't connect to anything we already know, or because abstract descriptions confuse us. So this series aims to give you explanations that are more direct and visual. Second, conciseness. This entire tutorial is about 2 hours long, with each video between 3 and 5 minutes, covering only the core concepts a beginner needs. Many teaching videos are long because they explain lots of minor details, things that aren't commonly used, but are still taught because they can be done. But at the beginner stage, spending time memorizing such details distracts from understanding core logic, and rarely used knowledge is easily forgotten. Real-world programming isn't a closed book exam. You don't need to memorize every language detail because you can always search online or check documentation. With more coding experience, you'll realize the real skill is knowing how to search for problems, find solutions, and solve them efficiently, not being a memory champion. As for why I chose Python as the language of instruction for the introductory tutorial, you can watch my other video, so I won't go into it here. I hope this tutorial gives you a light, friendly start, helping you grasp a core mindset of programming. After this, you can watch longer tutorials to fill gaps, do hands-on projects, or even learn another language. Once you master core logic, learning a second language becomes much faster. But for beginners, the most important thing is simply getting past the initial barrier. Before you write your very first line of Python code, there are 2 things you need to set up. The first thing is installing the Python interpreter. Your computer can't directly understand the Python code you write, so it needs an interpreter, basically a translator, to convert the code into bytecode before running it. Python works by translating one line and executing one line. So when we say installing Python, what we really mean is installing the interpreter itself. The second thing you need is a code editor. Just like we use Word to write documents, we also need a proper tool to write code. There are tons of editors out there, and the debate over which one is the best can easily start a war among programmers. I personally recommend PyCharm, made by JetBrains or JB, and it's designed specifically for Python. And PyCharm isn't just for writing code, it's actually an IDE, an integrated development environment. Besides smart features like code completion, auto-formatting, and spell checking, it also includes a debugger, version control tools, and more. But as a beginner, you don't need to learn everything at once. As you gain experience, you'll naturally start using more and more features. In the next 2 videos, I'll walk you through how to install both of these on Windows and MacOS. In this video, I'll walk you through installing Python and PyCharm on Windows. If you're not using Windows, you can safely skip this video. First, let's download Python. You can search for the official Python website in your browser, or simply go directly to www.python.org. Once you're on the site, click on Download, ensuring you download the correct version for your system. Next, click the big yellow button to start downloading the latest version of Python. If the version number you see is different from mine, for example, not 3.1, oh, that's totally fine. As long as it starts with 3, there won't be any major differences. Once the download is complete, open the installer to begin installation. Here's a very important step. Make sure to check Add Python to Path, so your system knows where Python is installed. Then click Install Now, and wait a moment for the installation to finish. If you see a message about path length limits, click it to resolve the issue. Then click Close to exit the installer. To verify the installation, search for CMD in the menu to open the command prompt. Type Python in lowercase and press Enter. If you see Python followed by the version number you installed and some additional text, that means Python has been installed successfully. Next, we'll install PyCharm. Search for the official PyCharm website. If the URL looks correct, go to Downloads and click the blue button. This site should also automatically detect your operating system and select Windows for you. Click the black download button to get it. Once the download finishes, open it and follow the installation steps by clicking Next. If you want a desktop shortcut, check that option. If you want PyCharm to open all Python files by default, you can check that option as well. Then click Next and wait for the installation to complete. PyCharm is a fairly large application, so the installation may take a little while. Click Finish and close the installer window. Next, launch PyCharm and go through the initial setup. First, accept the user agreement. As for whether to share anonymous usage data, either choice is fine. Now you've completed the PyCharm setup on Windows and are ready to create projects and start coding. In this video, I'll walk you through installing Python and PyCharm on a Mac. If your computer is not running MacOS, you can safely skip this video. I'll guide you through downloading the Python interpreter and PyCharm from official sources. First, download Python. Search for the official Python website. Click on the page marked as official. Alternatively, you can type the following address directly into your browser's address bar, www.python.org. After entering the site, click Downloads. You should see that the website automatically detects your operating system. For example, it should show for MacOS. This ensures that the downloaded version is compatible with your system. Next, click the large yellow button. This will start downloading the latest version of Python. If the version number you see is different from mine, that's completely fine. Once the download is complete, open the installer and begin the installation. You can keep clicking Next during the process. Then enter your Mac username and password. Administrator privileges are required for installation. The installation will then begin. Wait a moment for it to finish. Then close the installer window. To verify that Python was installed successfully, we need to open Terminal. Method 1 is to click the magnifying glass icon in the top menu bar, type Terminal, and open it. Method 2 is to open Finder. Then choose Go Y Utilities from the top menu, locate Terminal, and open it. Press Enter. If you see Python followed by the version you just installed, along with some additional output, that means Python is now installed on your computer. Congratulations! Next, we'll install PyCharm. Search for the PyCharm official website. If the URL is www.jetbrains.com/PyCharm, then you're in the right place. Click Download. You'll be taken to a new page. PyCharm used to have two versions, the Professional Edition and the Community Edition. The Professional Edition was paid, and the Community Edition was free. Now they have been merged into a single version. You can simply download this unified version. After downloading, you'll automatically get a 1-month free trial of the paid features. After the trial ends, you can continue using most features for free without subscribing. For pure Python development, the free features are more than sufficient. One more thing to note, check whether the chip type shown next to the download button matches your Mac. Checking your chip type is simple. Click the Apple icon in the top left corner. Select about this Mac in the window that appears. See whether the chip is labeled Intel or Apple. If your Mac uses an Intel chip, check whether it matches the version shown on the PyCharm download page. If it doesn't match, click the drop-down menu and switch to the Intel compatible version. It already matches, so I can click Download directly to download PyCharm. After the download finishes, open it, drag PyCharm into the Applications folder. It should now be located there. You can also search for PyCharm directly and open it. A window will appear asking you to select your language and region. Next, you'll need to accept the user agreement. I usually don't read it in detail. Then choose whether to share anonymous usage data. Either option is fine. Next, if your Mac shows a prompt asking for file access permissions, simply click Allow. Then, if you have other code editors installed, PyCharm will ask whether you want to import their settings. I don't need that, so I'll skip it. You've now completed PyCharm's initial setup on macOS. You're ready to create projects and start coding. Following the previous videos, You should have already finished installing PyCharm. Now you're ready to create your own project. First, open PyCharm. Now we're going to create a project so we can manage our code files in one place. On the welcome screen, find New Project and click it. The first line here shows the location of your project folder. You can change it to a location that's easier to find. For example, your desktop. But make sure you create a folder first and then select that folder. Otherwise, PyCharm will treat your entire desktop as the project folder, which can get very messy. Below that, for the interpreter type, you can keep the default project venv. PyCharm will automatically detect the Python version installed on your computer. If you have multiple Python versions installed, you can open the drop-down menu and select the one you want. Okay, then click Create. Inside every project folder, you should only put files related to that project. For example, in a website project, you might have front-end and back-end code, images, and other assets. Don't casually put things like ID photos or your thesis files into the project folder. PyCharm also automatically creates a folder called venv. This folder represents an independent Python virtual environment for the project. Its purpose is to allow different projects to use different Python versions and different third-party libraries. We'll talk more about third-party libraries later. For now, just remember one thing. Don't touch this folder, don't delete it, and don't put anything inside it. If you've made it this far, you've already surpassed 99% of people, because setting up a local development environment on your own computer is never easy. If you want to create other Python projects later, just repeat the same steps. You might be wondering how to start writing code, since there doesn't seem to be any editable area. To write code, click on the project folder, right-click, choose New, then select Python file, give it a name for example, and press Enter. Now you have a place where you can write and edit code. Writing code is less like talking to a computer and more like giving it instructions. As long as you have permission and your instructions make sense to the machine, it will follow them exactly. For example, if you ask a friend to shout, "I am fabulous," they would probably refuse, feeling awkward and shy. But a program will follow the command without hesitation. In Python, it only takes a single line. The computer will display, "I am fabulous." Let us break this code down. Print is the function Python uses to show content on the screen. Whenever you want the computer to display text, you put that text inside print. The parentheses are where you place the content you want to display. If you put the content outside the parentheses, Python will not show it and may even produce an error. Next, the quotation marks are also important. You can use single quotes or double quotes, but they must be ASCII quotes, and they wrap the text you want to display. This is just like a misunderstanding that often happens in English. If you tell a coworker, "Please write the word thank you next time," but you forget the quotation marks and instead say, "Please write thank you next time," they might take it literally and write the entire phrase, "Thank you next time." This is not what you meant at all. If you had written thank you, there would be no confusion. Programming works the same way. Quotation marks prevent ambiguity. Without quotation marks, the computer will treat the content as a variable rather than text. Inside the parentheses is the text we want to display, such as "I am fabulous." The text itself can contain any language, but the quotation marks and the surrounding symbols must be ASCII. The quotation marks and the text inside them together form a string, which is a sequence of characters. Even if the content is all numbers, once you add quotation marks, it becomes the string 666, not the number 666. Now let us try this on your own computer. Open PyCharm. The first empty project you created earlier should appear in the recent projects list. If it doesn't, you can click Open here and locate its folder on your computer. Or you can simply create a new one. In my case, I'll just double-click to open the project I created earlier. Click Project in the sidebar to show all the folders. Under this project folder, we're going to add a Python file. This was demonstrated in the previous video. First, select this folder. Be careful not to create it inside the venv folder. That folder is the project's virtual environment, and it should be kept separate from our code. So click the top-level project folder, right-click it, choose New, then select Python file, enter a name. I'll call mine wanter.print2demo, which indicates a Python source file. I recommend avoiding spaces in file names. For example, spaces or strange symbols like putting an emoji in the name. Stick to letters, numbers, and underscores. This helps avoid issues where files can't be found based on their file names. Press Enter to create the file. If this is your first time creating a file, ADI log may pop up asking whether to add the file to Git. At this beginner stage, you can ignore it. If it appears, select Don't Ask Again and click Cancel. Since I already chose Don't Ask Again before, it doesn't pop up for me anymore. Now in this file, write our print statement. Start with print, all in lowercase. PyCharm provides some helpful suggestions here. For example, when I type PR, it already suggests keywords. Then add parentheses, a pair of quotation marks, and type the content you want to print. Now the code is ready to run. You can right-click here and choose Run. You'll see the Run window at the bottom displaying the output. The content we wanted to print is displayed successfully. You can ignore the first and last lines. The lines above are generated by PyCharm when you click Run, showing the command it executed automatically. If the bottom line shows an exit code of 0, it means the program ran without errors. If there is an error, the exit code will be a non-zero number. These two lines are always shown by PyCharm every time you run the program, so you can ignore them. What you should focus on is the content between the first and last lines. The content inside the quotation marks can be replaced with anything you want. The result will be printed. If there's a problem with your code, for example, like this, PyCharm will automatically highlight the issue in red. When you run the code, you'll also see red error messages. For example, like this. And here, the exit code will also be a non-zero number. If you can't tell what's wrong, you can copy the red error message and paste it into a search engine. The lines above including your file name and code don't need to be copied. Everyone's code may be different, but the errors are often similar. So you can copy just that error line and paste it into a search engine. You'll find that many people have encountered similar issues, so copying error messages into a search engine can often help you solve the problem. Next, I'll teach you how to write more complex code. Printing strings has a few more advanced tricks, and here are the most common ones. First, string concatenation. A string, as we discussed in the previous video, is simply a sequence of characters wrapped in quotation marks. You can connect multiple strings using the plus sign to form a longer one and print it out. And because there is a space before the word "world," the printed sentence has a space in the middle. If you remove that space, the two words would stick together. Second, handling single and double quotes. In the previous video we said you can wrap strings in either single quotes or double quotes. In most cases, both work the same, but if the content itself contains quotation marks, then you need to be careful about whether the inner and outer quotes are single or double. This line of code will fail. The first quotation mark is fine, but when Python reaches the second one, it thinks that marks the end of the string, so it believes he said it's the entire string. Then it keeps reading and becomes confused. What is that supposed to be? So it reports an error, but if you change the outer quotes to single quotes, Python understands that the matching single quote is at the end, and everything inside, including the pair of double quotes, is part of the string. You can also do the opposite, outer double quotes and inner single quotes. That prints out the single quotes correctly. But what if a sentence inconveniently contains both single and double quotes? There is still a solution. You can place a backslash before the quotation mark inside the string. This tells Python that the quote is part of the content rather than the end of the string. It may look a bit messy, but it prints exactly like this, he said. Let's go. Every quotation mark that comes right after a backslash will be printed as is. This backslash is called an escape character. Whenever a backslash appears in a string, Python knows to read it together with the next character and treat it as something special. New line characters. In Python, you cannot split a line of code randomly. If you write it like this, it will produce an error. Python reads a line and executes it. When it reaches the end of the first line and sees that your quotation marks and parentheses are not closed, it assumes you forgot them. It does not continue reading the next line and throws an error immediately. If you want the hi to appear on the next line, you can use a backslash followed by n to represent a new line. This is another use of the escape character. The printed result places hi on the second line. Fourth, triple-quoted multi-line strings. If you want to print a poem, using the previous methods can get tiring. You would either need to add Taiwan at the end of each line or write several print statements. Since each print starts on a new line, here comes the powerful triple quote feature. 3 single quotes or 3 double quotes in a row. When you wrap your text in triple quotes, Python treats each new line as part of the content rather than the end of a statement. This makes printing multiple lines extremely convenient. Time to practice. I'm still working in the project we created earlier. I create a new blank Python file. Example 1 is string concatenation. We're using the familiar print function again. Inside it, you can put multiple strings and connect them with plus signs. For example, start with print, then add a plus sign. The spaces on both sides of the plus sign are technically optional. However, adding spaces makes the code more readable. But never add spaces randomly at the beginning of a line. Like in this example, PyCharm is already warning me about an error. The importance of leading spaces will become clear later on. Then add another string. Now let's run it. You can see the full sentence printed successfully. The space in the middle is because I added a space in the code. The second example is escaping single and double quotes. We're still using print. First, let's try without using a backslash to escape. As you can see, PyCharm is clearly showing an error here. That's because it treats this as the end of the string and doesn't know how to interpret the rest. So we add a backslash here. Now you can see the error warning is gone. The backslash and the following single quote are highlighted in the same color, indicating they belong together, which shows they work as a pair. What you need to note here is that this is a backslash, not a forward slash. The backslash key is located above the Enter key on the keyboard. A forward slash won't work here. Going back to the backslash. Let's run it. All right. You can see that Let's Go is printed successfully. Example 3 is the new line character. Let's try printing 2 lines. Let's print it and see what happens. You can see that the line break worked. The second line appears on its own line. You can also print just a new line character by itself. This will create an empty line. Example 4 is multi-line input using triple quotes. Let's start with print again, then use 3 single quotes or 3 double quotes. PyCharm is quite smart. When you type 3 quotes, it automatically adds the closing 3. Here, I'll call poem and paste it in between, then run the code. You can see that the line breaks are printed exactly as they were. After printing all of this content, you might wonder what the practical use is. On C, you learn about variables. You understand one of the key purposes of printing. See you in the next video. Here's a common situation. You have a piece of text you use all the time, like your partner's phone number. The string is long, say, 11 characters, and typing it repeatedly is a hassle, not to mention hard to remember. So naturally, you'd wonder, can I store it somewhere? In real life, we have contacts apps. You search a name, and the phone number pops up. The name acts like a label, and through that label you get the stored value. Variables in programming work exactly the same way. They store or refer to a value. To use a variable, you first give it a name. The name can't contain spaces, and it can't start with a number. And don't put quotation marks around it. If you do, it becomes a string instead of a variable. Then you add an equal sign, followed by the value you want to assign. This is called an assignment. It gives a variable its value. Once assigned, you can use a variable repeatedly without retyping the whole value. Also, Python executes from top to bottom. You must assign a variable before using it. Otherwise, you'll get an error. It's like asking your contacts app for a number you never saved. It has nothing to give you. The program isn't a fortune teller. It is not going to guess for you. And if your partner changes their number, or you change your partner, your MyLove value needs to change too. Easy, just assign it a new value with another assignment. A variable is called a variable because it can vary. Now the printed result will show the new number. You can also assign one variable to another. For example, if MyLove currently stores your ex's phone number, but you want to switch it to your current partner's number without losing the old one, what do? You create another variable. Say my exes store the old number there, then assign a new value to MyLove. On the second line, you use the value of MyLove to assign it directly to my ex. In an assignment, the left side is treated as the variable name, while the right side is evaluated first, producing the number starting with 137, which then gets stored into my ex. Finally, you assign a new value to MyLove, and now you've saved both your ex's and your current partner's numbers. As mentioned earlier, print becomes super useful when variables are involved. You can print their current values to understand what the program is doing. Now it's practice time. I won't use a phone number as an example here. It's mainly because it's too long and I don't feel like typing it. Now suppose we have a greeting message that says, "Hello, have you eaten?" For example, if we're greeting Jang-san, we print "Hello, have you eaten?" plus the name string, Jang-san. Then if we greet Li-Si, we again print "Hello, have you eaten?" plus the name string Li-Si. But if you need to greet many people, this "Hello, have you eaten?" string would have to be typed over and over again. So we can assign it to a variable. For example, we can let greet be equal to the string "Hello, have you eaten?" Then all the greetings below can be simplified into greet plus the name string. For example, like this. If you later want to greet someone else, such as Wang Wu, that's very easy as well. Just use greet plus the name string. Let's print it out and take a look. You can see that the output matches our expectations. Now, if we want to change greet, for example to "Yo, what's up?" you can simply replace it in the code. You can see that the advantage of using variables is that once you update the variable's value, every place where the variable is used will automatically change to the new value. For example, let's run it here. You can see all the greetings have changed to a different style. But you might ask, doesn't this mean we lose the previous greeting? Yes. Once a variable's value is replaced, the old value is gone. We can handle this another way. We can store the previous greeting first and then perform the replacement. So we can do it like this. And set it equal to the previous greet. Then create another variable and set it to our new value. Yo, what's up? Finally, update greet. Let's print it out and see. At the same time, we've preserved the greeting. For example, that's all for this video. As for how to name variables, are there naming rules for these? We previously mentioned that names can't contain spaces and can't start with a number. As for other rules or common conventions, we'll discuss them in detail later. After assigning a value to a variable, everything afterward depends on using the variable's name to access or update that value, so the name really matters. There are strict rules for naming variables. They can contain letters, digits, and underscores. Nothing else, no spaces, no symbols other than underscores. And they cannot start with a digit. If you break these rules, Python throws an error immediately, but no error doesn't mean good name. Variable names should be easy to understand and remember. If you name everything A or ABC, you'll probably forget what they mean a few days later. So what counts as a good name and what doesn't? In Python, the common convention is snake case, all lowercase letters, words separated with underscores. For example, user age, user gender. Wherever English would normally use a space, snake case uses an underscore. There are other naming styles, like camel case, which uses capital letters to separate words, but Python generally prefers snake case for variables. Two more important notes. Faraday variable names are case sensitive. User age and user age are two different variables. Avoid using Python keywords as variable names, such as print. If you assign something to print, say a string, you lose the ability to use the real print function in that program because the name is now overwritten. Python has around 30 keywords. You'll naturally become familiar with them, so there's no need to memorize them up front. PyCharm highlights keywords with special colors. If your variable name suddenly appears colorful, it's probably a keyword, so change it. That's enough for now. See you in the next video. I don't know if you've had this happen before. You are entering a long expression into a calculator or phone. Halfway through, you feel like you might have tapped the wrong key, and suddenly you're stuck. Do you continue or clear everything and start over? There's also the situation where you simply forget where you were in the calculation. Super frustrating. If you use Python for math, you can avoid all of this. Your code easily beats any calculator. In Python, integers are a different type from strings. They're plain numbers, no quotation marks. If you add quotes, they become strings and can't be used for math. Python also has a type specifically for decimals called floating point numbers. Numbers with a decimal point are floats, and numbers without one are integers. Now let's talk about math operations, starting with the classics: addition, subtraction, multiplication, and division. Addition and subtraction exist directly on the keyboard, but the mathematical multiplication and division symbols don't, so Python uses the asterisk for multiplication and the / for division. And it must be the / the one left of the shift key, not the \, which is used for escape sequences. So if we want to write 1 + 2 - 3 divided by 4 × 5, it looks like this in Python. Quick challenge, no prize. What's the result? If your answer is 0, then you need a refresher on operator precedence. Python follows the same precedence rules as standard math: parentheses first, then exponentiation, then multiplication and division, and finally addition and subtraction. Exponentiation in Python uses 2 asterisks, asterisk, asterisk. If you want 2 to the power of 3, you write it like this. And yes, calculators can do more advanced operations like trigonometric functions, logs, square roots. Can Python handle those? Absolutely. Code doesn't lose first. You need to import a module called math. Think of each module as a toolbox, where every function is a tool for a specific job. For example, print is a function too. It outputs text. But you don't need to import it because Python includes it by default. Such functions are called built-ins. The math module, however, is specifically filled with mathematical functions. To import it, write import math at the top of your file. Then you use math followed by the function name to access its features. For example, to calculate the sine of 1 radian, you write math. Scene 1, you cannot omit the math part because the function belongs to that module. How do you know what other functions the math module supports? You can look up the official Python documentation for the math module. It lists all available functions. For example, if the doc say math, log2 returns base -2 logarithms, then the log base 2 of 8 is written as math, log2 8. But if you write an expression directly in your script and run it, you'll notice nothing prints out. That's because Python does compute the result and store it in memory. But since you didn't use it or print it, you never see it. So to see the result, you must use print or assign the result to a variable and then print that variable. Now it's practice time. Our goal is to write a quadratic equation root calculator, for example, to calculate the 2 real roots of -x² minus 2x plus 3 equals 0. We can use the quadratic formula. I have already forgotten this formula. I just looked it up. First, we assign variables in the code because here it is plus or minus. There are 2 solutions. We can calculate them separately. First, calculate the solution with addition, which is -b plus the expression under the square root is b squared. Minus 4 times a times c squaring is represented by 2 asterisks. Then the question comes, how do we write the square root in code? A square root is equivalent to the 1/2 power, so it can be written in this way, or you can use a function called cqrt from the math library, which also returns the square root. This is written in the documentation. If I want to use this security function, first I need to import math at the top of the file. Then use its function here. The library name comes first followed by a dot. then comes the function name, which is security, then continue back to our formula. Because division comes next, we wrap everything above the fraction line in parentheses, divided by 2 times a. Okay, this is our first solution. And the second solution only needs the plus to be changed to minus no moment of truth. If you run it, you will find nothing appears because, as mentioned before, you need print. To see the result, the print also needs to wrap the entire expression. Then click Run. At this point, you can see the 2 correct outputs. If you want to solve another equation, you do not need to change the formula at all. You only need to update the variable values above. For example, if we calculate x squared plus 9x plus 20 equals 0, just run it. Direct result is shown again. To summarize, doing math with code has the following 3 advantages. First, you can see the entire formula. You can check it anytime without worrying about mistakes. Second, it is very easy to change variable values. There is no need to retype the formula. Third, if the formula is complex, you can break it into steps using intermediate variables. For example, let b squared minus 4ac equal delta, then you can directly write the square root of delta. The output should still be the same. This makes the process cleaner and clearer. This video contains many knowledge points. The next video will be more relaxed. See you later. There's a joke that one of the things programmers fear most is this: when you finish writing your code, only you and God know what it does. A few days later, only God knows. To avoid this, programmers usually add comments when writing code. A comment is 1 or more lines of text that the interpreter or compiler completely ignores. It's for humans to read, not for the machine to execute. All a major purpose of comments is to explain the reasoning behind code, helping others or your future self understand the intention. In Python, comments start with a hash number. Anything after the number is ignored and never executed. But the hash only works for a single line, so for multi-line comments, you need a number at the start of each line. Besides explaining code, comments can also be used to temporarily disable code without deleting it. Just add a number in front. If the code block is long and you don't want to add number manually, PyCharm has shortcuts. Select the entire block and press Ctrl+5 on Windows or CMD+4. On Mac, PyCharm will automatically add number to every selected line. Pressing the shortcut again removes them. Another way to make multi-line comments is to wrap them in triple quotes. You might wonder, didn't we use triple quotes earlier for multi-line strings? Yes, but if you don't print it, assign it, or use it in an expression, it has no effect, so it behaves just like a comment. That's why many people use triple quotes as multi-line comments. Since comments don't affect program execution, some programmers get creative, writing jokes, prayers for bug, free code, or dramatic warnings to future developers. Comments have even caused PR scandals. In 2017, a developer at Xiaomi Music labeled free VIP users as poor VIPs in a code comment. When users discovered it, it caused backlash, and the developer had to apologize, saying they would write proper comments from now on. So yeah, try not to go too wild with your comments. In Python, these categories are called data types, which include strings, integers, floating point numbers, booleans, the null type, and later on, lists, dictionaries, and more. The string type str is a sequence of characters that represents text. It's typically wrapped in either double quotes or single quotes. You can use the len function on a string to get its length. When calculating the length, spaces, numbers, and symbols each count as one character. But note, if there's an escape sequence, like a backslash followed by n for a new line, the entire escape sequence counts as just one character. You can also extract a single character from a specific position in a string. By placing square brackets after the string and putting an index inside, you can pull out the character at that position. Think of the index as a position number, but unlike in daily life, in programming we start counting from 0. The first index is 0, the second is 1, and so on. So if I want the fourth character, I'd use index 3, which would give me the character L. The integer type in Python is int, and floating point numbers are called float. Operations with these were already covered in the earlier video on math in Python. Since number notation and arithmetic are fairly intuitive, I won't go into detail again here. The Boolean type, bool, only has two possible values, true and false. True is written as true with a capital T and false as false capital. Even though Booleans only have these two values, you'll soon see how essential they are when we get to logical conditions. For now, just remember they exist. There's also a special type called the null type, none type. It has only one possible value, none. None is not zero, not an empty string, and not false. It means no value at all. If you know you'll need a variable but don't yet know what value to assign, you can start by setting it to none. Now it is practice time. First, let's try finding the length of a string. Define a variable a and assign it the value hello world. Then we can use the while function to get its length. If you run the code now, you'll still see nothing because we need to use a frame print title to see the returned value. Run it again now, and you'll see the result is 12. This is because spaces and punctuation marks also count as one character each. Next, let's try accessing individual characters from the previous string using indexing. Always remember that indexing starts from 0. So if we want to get the letter H, we should use index 0, not 1. Print it, run the code, and you'll successfully retrieve the first character. What's the index of the last character? Since the total length of the string is 12 and indexing starts from 0, 0, 1, 2, 3, and so on, the index of the last character should be 11. Print it to see. Yep, you successfully get the exclamation mark. Alternatively, you can combine it with the silent function, where the index is the string length minus 1, and you'll get the same result. Now let's define some Boolean type data. Assign the variable fun_db1, the value true, and the foo2, the value false. Their first letters must be capitalized. If you use lowercase, Python won't recognize them as Boolean values. Look, an error has already appeared. Also, don't wrap them in quotes, or they'll become strings. Let's revert them back to Boolean types. Next, define a variable of the null type. Set tween to null. The first letter n must also be capitalized, otherwise Python won't recognize it. Now, to verify the types of the variables we defined earlier, we can use the type function, one by one. For example, type pipe r, where ia is the first string we defined. Let's print it and see. It shows the string type. Then try type b1. Printing it should show the Boolean type. For typen, since 到丙 n 到8type, it should print 代币 none type. You can also use type by on the floating point numbers and integers we learned earlier. For example, type 1.5 since there's a decimal point. It should be the floating point type, float type, not the integer type, int. Finally, let's see what happens if we use a function on the wrong type. For example, if we try to use the filen function on the Boolean value ibb1, running the code will show that Python directly reports an error. Therefore, understanding the type of the object you're working with is crucial. Python has two execution modes, command line mode and interactive mode. Up to now, we've been using command line mode, writing code in a file, saving it, and then running the whole file. When the program runs, the Python interpreter reads and executes the file line by line. And because Python doesn't need to read the entire file before executing a single line, there's another mode, interactive mode. You type one line, Python immediately runs it and shows you the result. The first advantage of interactive mode is that you don't need to create any files. You simply enter an interactive environment, like clicking the Python console in PyCharm or typing Python 3 in CMD or terminal. You'll see 3 angle brackets, which means Python is waiting for your command. You can type any Python statement, for example, print hi, press enter, and Python immediately prints hi. The second advantage of interactive mode is that you don't need a print statement to see results. For example, in command line mode, if you define a equals hello plus, you need print a. To view the value in interactive mode, typing a and pressing enter directly shows it. Similarly, for 3 times 2, you would need print 3 times 2 in command line mode to see the result 6. In interactive mode, Python evaluates it and displays the 6 automatically. To exit interactive mode, type quits and press Enter, or press Ctrl+D. Although interactive mode has these benefits, we still mainly use command line mode. The reason is simple. Interactive mode doesn't save your commands, so once you exit, everything disappears. Some people describe interactive mode as a playground. You can try things freely and immediately see what happens. When I need a quick one-off calculation, I just open interactive mode, type the expression, get the answer, and close it. While others are still looking for their calculator, doing it this smoothly in Python looks pretty slick. While programmers usually control the logic and results of a program, we often need information from the user so we can return personalized output. Python's inputs function lets you read whatever the user types. You call it by writing input and putting a message inside the parentheses to prompt the user. By now you know the pattern, a function name, parentheses, and arguments inside. That is the standard way to call a function. So what can you do with input? For example, you can ask the user for their age. When the program runs, Python shows the prompt and waits for the user to type. If the user types 20 and presses Enter, Python continues running the next lines of code, but just calling input doesn't tell you what the user entered. Fortunately, input returns that text, so you should store it in a variable. Once you have the value in a variable, you can use it for whatever logic you need. One important detail: import always returns a string, even if the user types a number. So if you try to do math directly with user age, Python will complain. What do you do then? Python provides an int function that converts a string into an integer. For example, int 666 returns the number 666. Just make sure the string actually represents a valid integer, otherwise int will throw an error. Similarly, floats converts a value into a decimal number, and str turns any value into a string. If you want to print a number together with text, you need to convert the number to a string first, otherwise Python will throw an error. So in our example, if you want to do math with the user's age, convert it to an integer with int first. And if you want to print the result along with text, convert that result back into a string with str. So if the user enters 20 and presses Enter, the program will output, "You will be 30 years old in 10 years." And now it is practice time. We can use input to build a simple BMI calculator for users. BMI stands for Body Mass Index. Its calculation formula is BMI equals weight divided by height squared. Weight is measured in kilograms and height in meters. First, we define a variable user weight and set it equal to the user's input for weight. We'll prompt the user, "Please enter your weight in kilograms." Then we define user height and set it equal to the user's input for height in meters. Next, we define user BMI, which equals weight divided by height squared. Now here, as you can see, Y's pie chart is already hinting at a problem. Currently, user weight and user height are strings, so we can't directly divide or square them. We need to convert both into numbers first. And note, we cannot use int for height, otherwise everyone would be 1 meter tall. So instead, we use the float function to convert the strings into floating point numbers. This way, we can calculate the BMI value. Finally, we can print the result for the user. If I write it like this right now, it will still cause an error, because remember, we also need to convert the number back into a string before printing. So let's use the str function one more time. Now we can run it and give it a try. Enter some numbers and it runs successfully. Now this simple calculator can compute the BMI for any height and weight. Anyone with even a bit of social awareness makes constant judgment calls in daily life. For example, someone might decide whether they can play games tonight based on their partner's mood, or an employee might read their boss's expression before deciding whether it's a good moment to ask for a raise. Deciding what to do based on whether a condition is met is exactly what conditional statements do. Python's conditional statements follow a simple structure. They start with if, followed by a condition. Any expression that evaluates to a Boolean, true or false, can be used as a condition. If you define a variable that stores a Boolean value, you can use it directly after if. For example, a variable like is I happy equals true or false can be used as the condition. You can also use comparison operators. Equality checks use equals equals because the single equals is used for assignment. For example, 3 equals equals 3 returns true, while A equals equals B returns false. The not equal operator equals returns true for A equals B. Other comparison operators, greater than or equal, less than, and less than or equal, behave just like in math. A condition like 5 n equals 20 is perfectly valid because it evaluates to false, which is still a Boolean. Don't forget the colon after the condition. The indented lines below it run when the condition is true. You can have multiple lines, and everything indented under the if belongs to the true branch. If you want nothing to happen when the condition is false, you can stop there. But if you want code to run when the condition is false, add an else, and indent the lines below it. Python relies on indentation to determine which lines belong to the if, which belong to the else, and which lie outside the entire block. And now it's practice time. We can combine input 2 to write a program that decides whether your partner will be angry if you play games tonight. First, define a variable for mood index, representing the mood score. Set it equal to the return value of the phone2 function. What's your partner's mood today? Please enter a mood index. Next, we'll use this value to determine whether you can play games tonight. Suppose if the mood index is greater than or equal to 560. It means things are still okay. Your partner can calmly tolerate you playing games all night. Then we can see print 2. Congratulations! You can probably play games tonight. Writing it like this could already be the end, because as mentioned before, the TVLSI part is optional, but actually, there's a problem with this program. Don't forget the 40 input_d function always returns a string. If we want to compare the string foimood indexi with a number, we need to convert tenmood indexi into a number first. So here we still use the fundata function to convert it into a number. Then we can also add the funilc part, colon, press enter. Still, don't forget the indentation, although PyCharm will automatically indent for you. Here we can also print a message. The condition for running this line is when foimood index imo60 is bullseye, which is essentially the same as imood index i60t. Now we can run it and try it out. First, enter a number for a pretty good mood, say 85i. You can see it prints, you can play games tonight. Let's run it again and try entering a not so good mood number, 20. It prints, better not play. Also, as mentioned before, the block under a condition can have more than one line. You just need to remember the indentation. For example, if you can play games, I can also add an emoji here to express a cheerful mood. If you don't indent properly, there will be a problem, because Python sees this line isn't indented, so it thinks the conditional block has ended. Then this line will be printed no matter what. Then below it, Python sees a -d elsein, but typeint exists independently of a foo, so Python will raise an error. Now let's fix the indentation and run it again to test. You can see the second line is printed too. Last time, we talked about how conditional statements decide what to do based on whether a condition is met. If the condition is true, Python runs the code under if. If it's false, it runs the code under else. But sometimes one condition isn't enough to decide what should happen. For example, if your partner is in a bad mood, you usually wouldn't dare spend the whole night gaming. But if they're in a bad mood and happen to be out hanging with friends, then your gaming freedom magically returns. That's when nested conditionals come in handy. A nested conditional simply means putting one if statement inside another. For example, you write one if first and inside it indented. You write another if. For the inner code, let's call it action A to run. Condition 1 must be true. Otherwise, the second condition won't even be checked. And of course, condition 2 must also be true. You can also add an else to that inner conditional. In that case, action B runs only if condition 1 is true and condition 2 is false. With nested conditionals, indentation becomes even more important. Python uses 4 spaces per level, and it relies on that indentation to understand which branch each line belongs to. You can also attach an else to the first condition. That block runs whenever condition 1 is false. Using nested conditionals, our earlier example would look something like this. If your partner's mood score is below 60, then check if they're home. If they're home, no gaming for you. If they're not home, congratulations, freedom unlocked. Instead of nesting, you can also use multiple conditions with elif, which lets you split behavior into more detailed cases. Python checks each condition from top to bottom and executes the first one. That's true. You can have as many elif statements as you want. No limits. This structure is often clearer and easier to read than deep nesting. And since Python executes from top to bottom, it only runs the first matching branch. So if condition 2 and condition 3 are both true, only the code under condition 2 runs. And now it's practice time. We can combine multiple conditions to enrich the BMI calculator we wrote earlier. First, let's copy the code from the previous Python input video that calculates the BMI value. If you've forgotten what that code does, essentially, it collects the user's weight and height, converts them to floats, then uses the BMI formula, weight divided by height squared, and prints the calculated result. According to the adult BMI classification standard, if the result is less than or equal to phi 18.5, it's considered underweight. If it's greater than psi 18.5 and less than or equal to phi 25, it's I normal. If it's greater than 25 and less than or equal to 30, it's die overweight. If it's greater than 30, it's die obesis. We can use multi-condition logic to output the corresponding classification for the user. First, if we see user BMI is less than or equal to 18.5e, output, this BMI value is in the underweight range. If we only had two cases, less than C 18.5 and greater than or equal to phi 18.5e. But since we now have multiple ranges, we need to use VC alifi. How should we write this condition? In math, we can write something like CAX, CAKX equals B to express a range. This notation is also valid in Python, so we can use it directly as a condition. Then output, this BMI value is in the normal range. Next, same idea. If it's greater than 25 and less than or equal to phi 30, output, this BMI value is in the overweight range. For the last condition, if all the previous conditions are false, that means the BMI is greater than 30. Meaning, if none of the earlier conditions match, output, this BMI value is in the obese range. Now we can run it and give it a try. Enter any weight, then any height, and you'll see it already outputs the correct BMI category. If you'd like to enrich this calculator further, you could try using nesting. For example, based on the user's gender, you could output hello, sir, or hello, madam before displaying the BMI classification. Last time, we talked about using nested conditionals to check multiple conditions. For example, if your partner's mood score is below 60, then check whether they're home that night. If they're home, no gaming. If they're not home, game on. Too nested, if statements can express this perfectly, but in some situations, things get more complicated and involve even more conditions. For example, let's imagine your partner will only be in an amazing mood, good enough to gift you a Nintendo Switch for New Year. If you've done over 10 chores this month, sent gifts more than once, gone shopping with them over 4 times, and haven't made them angry even once. If you try to express all that using nested conditionals, the code becomes extremely not elegant. Too much indentation, and you'll get lost instantly. That's when logical operators become useful. Python only has 3 logical operators, and, or, and not in plain language, and means both. XI5 and XSA10 means x is greater than 5 and less than 10, or means either XI55. 5 or XSA10 means x is either greater than 5 or less than 10. Not means not. Not XSA5 means x is not greater than 5. You can use and to connect 2 or more conditions. All of them must be true for the result to be true. If even one is false, the whole expression becomes false, or returns true if any condition is true. It only returns false when all conditions are false. Not works on a single value. If the value is true, not makes it false. If it's false, not makes it true. Not as straightforward. It just flips the Boolean value if you struggle to remember an and/or. Think of it this way. Pretend true is a happy event and false is an unhappy one. And it's like a pessimist if anything is unhappy. The whole thing becomes unhappy. Or it's like an optimist. If anything is happy, the whole thing becomes happy. You can also mix logical operators, but then you must watch for precedence. Not runs first, then and then, or. Of course, parentheses let you change the order, just like in math. Using logical operators, the earlier example can be written much more clearly. It's far cleaner than the nested version. But logical operators aren't always the best choice. You pick based on the situation. When a big sale season is coming, how do you keep track of all the things you want to buy? If you only want to buy 2 items, you can define variables like item 1 and item 2 and assign them the items you want. But if you want to buy 10 items, defining 10 variables one by one quickly becomes annoying. To solve this problem in a cleaner way, we need a data structure that groups related data together. Python lists are designed for exactly this. An empty list is represented by a pair of square brackets to put multiple values into a list. Wrap them in square brackets and separate them with commas. To add items to an existing list, you can use a list method called append. Methods are similar to functions in that they perform specific tasks. The difference is that methods are called on an object using a dot, while functions are called directly by name. Only important difference is that lists are mutable, while types like strings, numbers, and booleans are not. What does that mean exactly? Take strings as an example. The upper method returns a new uppercase string, but the original string stays unchanged. If you want to update the variable, you must assign the new value back to it. It returns a new string, while the original string stays unchanged. So if you want to actually update the variable, you must assign the new value back to it. Lists, however, are mutable, and append directly modifies the original list. That's why you should not reassign the list when using append. To remove an item from a list, you can use the remove method. Just to make sure the item actually exists in the list, or Python will raise an error. You can print a list at any time to see what it contains. Python lists can store values of different data types. Like strings, lists also work with the len function. Len returns the number of elements in the list. You can access list elements using indexes, which start at 0. The index of the last element is the length, -1. You can modify an element by assigning a new value using its index. Python also provides many useful built-in functions like max-min, and sorted returns a new sorted list without modifying the original one. These functions are extremely useful in real-world programming. Now it's practice time. Let's use a shopping list example to see how lists work in practice. First, define an empty list called for shopping. An empty list is represented by a pair of square brackets. Suppose the first 2 items on the list are a keyboard and keycaps. We can use the var append method to add them. Now let's print a list to see what's inside. Both strings should appear in it. If we want to remove the keycaps from the list, we can use a list name, followed by a dot, then var_move, and put the value inside parentheses. Print the list again, and the keycaps should be gone. Let's try adding a few more items, like speakers and a gaming chair. At this point, we can use the findFun function to check how many elements are in the list. It should output var_delivery. If you want to access an element at a specific position, you can use its findXOin. For example, to see only the first item in the list, you'd write tprint shopping list 0, because in programming, counting starts at t0. Now imagine you realize you can't afford the speakers and decide to replace them with a hard drive. You can also use the index to update the second element to hard drive. Remember, the second element has an index of 51. Print the list once more. The speakers should now be replaced with hard drive. If you also define a separate list of prices, say 57.99 for the keyboard, 510.24 for the monitor, 4200 for the hard drive, and Cyanide 100 for the gaming chair, you can use the function to get the highest price from the list. Similarly, you can use findMean to get the lowest price. And if you want to sort the prices from low to high, you can use the findSorted function. Just pass in the list, and it returns a new sorted list. Let's print all of these out: the highest price, the lowest price, and the sorted list. As you can see, Python can handle finding the maximum, minimum, and even sorting, all for you. How can we implement a context list in code? The key feature of a context list is being able to look up a phone number by a person's name. You could technically do this with variables. For example, to store Henry's number, you could assign it to a variable called phone number for Henry. To store Mary's number, you create another variable like phone number our number. Whenever you need someone's number, you just print that variable, but the problem is that this quickly gets messy. As the number of people grows, phone numbers end up scattered everywhere. So we need a data structure that can store all phone numbers in one unified place. What about using a list, which we learned earlier? If we use a list, we do end up with something that looks like a contacts list. But a list of phone numbers alone doesn't tell us who each number belongs to. That completely defeats the basic purpose of a contacts list, looking up numbers by name. What we really want is to bind names and phone numbers together. This is exactly what dictionaries can help us do. A dictionary is used to store key-value pairs. The key is called a key, and the corresponding data is called a value. Each key maps to a value, and we use the key to look up that value. This works just like a real-world dictionary. You look up a word as the key and get its definition as the value. An empty dictionary is represented by a pair of curly braces. To store multiple key-value pairs, you put them inside curly braces, connect keys and values with a colon, and separate pairs with commas. To get the value for a specific key, write the dictionary name followed by square brackets containing the key. One important rule is that dictionary keys must be immutable. Lists are mutable, so they cannot be used as dictionary keys, strings, integers, and floats. On the other hand, work just fine. But what if your contacts list has 3 people all named Mike, and you need both name and age to tell them apart? Lists can't be keys, so what do? Python thoughtfully provides a data structure that's immutable, but looks a lot like a list, the tuple. Tuples can hold multiple elements too. Visually, lists use square brackets, while tuples use parentheses. Because tuples are immutable, you can't add or remove elements from them. That lack of flexibility is exactly what allows us to store multiple Mike entries in a dictionary. In this case, those tuples become the dictionary keys. When looking up a phone number, you use the entire tuple as the key. Like lists, dictionaries are mutable, so you can add and remove key-value pairs. For example, if you get a phone number from someone new and want to add it to your contacts, you can assign a phone number to a new key using square brackets. This adds a brand new key-value pair to the dictionary. But be careful updating a value uses the exact same syntax. If the key already exists, this operation will overwrite the original value. You gain a number, but you also lose the old one. If you want to check whether a key exists, you can use key in dictionary, which returns a boolean. It returns true if the key exists and false otherwise. To delete a key-value pair, you can use del. Write del followed by the dictionary name and the key in square brackets to remove both the key and its value. If the key doesn't exist, Python will raise an error. If you want to know how many entries a dictionary has, the good old lend function still works. And now, it's time to practice. We can create an electronic dictionary for looking up internet slang and popular phrases using a dictionary. This exercise will combine dictionaries with previously learned to input and do full statement, input and die full statements. You can search for some English slang terms online. First, create an empty dictionary. We can pre-populate the dictionary with 2 entries. The method is key, followed by the corresponding value. For example, I'll add the entries for goat and sleigh. Separate the next key-value pair with a comma, and it is recommended to break the line for clarity since it is a bit long. After line breaks, each entry will be clearer. Now we've created a dictionary with a length of 2. Then, add the following slang terms and their definitions to the dictionary one by one. You can search for more, such as cap, based, sus. The way to add them is dictionary name, square brackets, put the key inside, and assign a value to it. Now our dictionary has 5 entries. Adding them one by one is a bit slow, so I'll use some editing magic. Alright, now my dictionary has 10 entries, and we can start implementing the lookup feature. Our lookup feature works like this. First, ask the user, please enter the slang term you want to look up. Also, remember to assign it to a variable, such as byquery, otherwise we won't be able to capture the user's input. We need to know if the queried term exists in our dictionary. Here, we use FIMA to check. If the key is in the dictionary, first print it for the user. Print a line like, the meaning of query is as follows. Then, we print the meaning of the term for the user. How do we get the definition of toquery? It is the dictionary name, square brackets, and the key name. But here, we have a variable, so we put toquery inside. This is equivalent to using the user's input to look up its corresponding value in the dictionary. If the queried term is not in the dictionary, we first print for the user. Sorry, the slang term you queried is not yet included. Then, we inform the user how many entries are currently in our dictionary. Here, a reminder, we need to use the vylen function. Currently, this dictionary contains entries. To get the length of the dictionary, use vylen with the dictionary name inside. But note that vylen returns an integer, so we need to convert it to a string in order to concatenate it with a previous string. Let's say I want to look up the meaning of goat. You can see it successfully prints the meaning of goat, because I have that entry. Now, let's try a non-existent slang term, like ASDF. You can see it also tells me, sorry, the slang term you queried is not yet included. And it successfully prints how many entries are currently in the dictionary. Imagine you have self-reported temperature data from tens of thousands of employees, and you need to find out whether anyone has a temperature above 38 degrees Celsius. If you check them one by one, the pandemic might be over by the time you finish. In Python, we can use a swivel loop to iterate, and the iterable can be a list, a dictionary, a string, and so on. Iterating over a list means doing something to each element in order. Iterating over a dictionary means doing something to each key or value in order. Iterating over a string means doing something to each character in order. The basic structure of a Python for loop looks like this. First, a keyword metaphor, then a variable name you choose to represent each item in the iterable, followed by the keyword intent, and then the iterable itself. For example, if we want to check a list of temperatures, we can write it like this. Here, temperature lister is a predefined list containing everyone's temperature data. Temperature is just a variable name you choose. It doesn't matter what you call it. This variable will be assigned each element in the list, one by one, until the last one. The operations you want to perform on each element go on the next indented line. Any indented line is considered part of the for loop and will be executed once for each element. For example, to check each temperature and print, we're in trouble if it's above 38 degrees. You could write it like this. This way, you can simply count how many times the message is printed to know how many people have a fever. However, this still doesn't tell you exactly who has a fever. If you also have a dictionary that uses employee IDs as keys and temperatures as values, you can use a for loop to filter out the people with fevers. A Python dictionary provides 3 useful methods. Dikeys returns all the keys, values returns all the values. Items returns all key-value pairs. We can combine a for loop method to print out the employee IDs of people who have a fever. Here, the for loop uses 2 variables because multiple of a key and a value. This syntax assigns the first element of the tuple to phi and the second to phi temperature. If this doesn't feel intuitive, it means the same thing as writing it in this more explicit way. Running this program instantly finds all employee IDs with a temperature greater than or equal to 38 degrees Celsius. A for loop combined with for deranging can do some powerful things as well. When the great mathematician Gauss was in elementary school, his teacher asked him to compute the sum of numbers from 1 to 100. He immediately came up with the formula and got the result 5050. For those of us who aren't Gauss, manually adding 1 plus 2 plus 3 all the way to 100 even, in code is still pretty tedious. This is where a for loop with for the range really shines. Range represents a sequence of integers. The first number is the starting value, and the last number is the ending value. One important detail is that the ending value is void node included in the sequence. For example, insert for I in range 5, 10.b will take on the values from 5 to 9, but tevi no to 10. Range cv can also take a third parameter called the step, which controls how many numbers you skip each time. If you don't specify it, the default step is 1. For example, if you want to print all the odd numbers between 1 and 9, you could write it like this. With this approach, Gauss's little problem, summing the numbers from 1 to 100 becomes trivial for us too. First, we define a variable to store the result of adding 1 plus 2 plus 3, all the way up to 100. Then inside the for loop, for the I is 1 in the first iteration, so 1 is added to for the total. In the second iteration, for the I is 2, so 2 is added and so on, until all the I reaches 100. After the loop finishes, we print the value of for the total and get the answer we want. Imagine you want to capture an entire sunset with a camera, but you don't want to stare at it the whole time. So you decide to write an automated program that keeps taking photos until the sky brightness drops below 55. 100 byte. But how do we write this? Let's assume we have a function called fiMeasureBrightness that can measure the current brightness of the sky. If we only use andava statement, there's a problem. The program will check the condition only phi onset take at most one photo and fail to capture the whole process. What if we use alpha for loop to repeatedly run the for check that would run the check? Say 400 times, which sounds better. But computers run extremely fast, and even 100 iterations may still finish long before the sunset is over. The real problem here is that we don't know for how many times c. The condition needs to be checked before it becomes false. But that's okay. The while loop comes to the rescue. Its basic structure looks like this. The keyword while followed by a condition. As long as the condition evaluates to a Boolean value, either twi, true, or false, it can be used. The computer checks whether condition A is true. If it is, it executes the indented code below, then checks the condition again. If it's still true, it executes the action again, repeating this process until the condition becomes false and the loop exits. If the condition after findY is already false on the very first check, then the body of the loop will not run even once. Writing our sunset photo program with a findY loop becomes very simple. The program keeps taking photos as long as the sky brightness is I greater than or equal to 500 and stops once it drops below 500. This example shows that when you don't know in advance when a condition will end, a while loop is more suitable than a for loop. That said, in many cases, for while loops and for loops can be converted into each other. For example, the following three programs all print every element in a list. The first one uses a simple and straightforward for loop. The second one combines a for loop with for range. When string range is given only one value, the starting value defaults to phi0 and the ending value is that number. Here, the length of fill list 1, in this case, is assigned the values to 0 and so on, up to fill less than the length of fill list 1. Since die0 is the index of the first element and the phi length -1 is the index of the last element, this program effectively prints all elements in the list. The third example uses a while loop. At the start, die is initialized to phi0. Since I0 is less than the length, the loop runs and prints the first element. Then 9 is incremented. The loop runs again, and the next element is printed. This continues until high becomes by equal to I the length of the list, at which point the condition I high than list 1 becomes false, and the loop exits. From these three examples, when both dive for and dive while loops are possible, the dive for loop is usually simpler, more intuitive, and requires fewer lines of code. Also, dive loops are generally more dangerous than dive for loops. For example, if you forget to increment dabi, the program may enter an infinite loop because dabi I stays at I0 and the dive while condition remains true forever. To sum up, for loops are more convenient when you know exactly what you're looping over or how many times to loop. For a while, loops are more general, especially when you don't know how many iterations are needed. And now, it's practice time. We can use looper to write a calculator that computes the average of numbers entered by the user. The special feature of this calculator is that the user can input any number of values, and finally enter foi, the letter Q, to indicate they're done. Then the program calculates and displays the average. You can pause here and try to write it yourself first, then play the video again to see my reference code. First, let's have our calculator print, "Hey there, I'm an average calculator." Then we take input from the user. Please enter a number. And add a hint. After entering all your numbers, enter swy the letter Q at the finish. We also need to remember to assign the string returned by only input to a variable, otherwise we won't be able to use what the user typed. Now the question is, how do we keep getting input from the user until they enter swy the letter Q? This kind of scenario, doing something repeatedly until a condition becomes false, fits perfectly with the asterisk while loopy we can write. Should it be equal to equal, the letter Q, or not equal to eva, the letter Q? Think about it. We want to keep looping while the input is warnote, the letter Q, so we should check first. Then inside the loop, we can get the user's next input by copying that to put the line here again. Let's run a quick test first. You'll see that as long as the input isn't the letter Q, the program keeps asking for more. If it is the letter Q, the loop ends and the program finishes. Now that we have the core loop logic, the next step is calculating the average. To compute the average, we need the sum by of the numbers and the sum by counter of numbers. Average IB equals sum by D divided by count. So we can define a variable sum total to keep track of the sum and the sum by counter to track how many numbers were entered. Next, each time we get a valid input from the user, we should update both total and count on part. But where should this update happen? It should definitely be stored inside the for while loop. Otherwise, it would only run once. If we place it after the line that gets the user's new input, then the very first number entered won't be added. Also, if the user enters phi the letter Q at that point, trying to add phi the letter Q to total will crash the program. So let's put the update 2x4, asking for the next input. First, convert the user's input into a decimal number. Then add it to photo. This line can also be shortened. It means exactly the same as. Let's replace it with a simpler version. Similarly, so we'll use that simpler form too. Now the program can correctly accumulate the sum and count of all numbers entered. Next, we calculate the average. Just need to print it out. Print the average of the numbers you entered is result. But there's still a potential issue if the user enters the letter Q right at the beginning. C total would be 0 and counter would also be 0. Then 0 divided by 0 is mathematically undefined. Python won't allow it and will throw an error. So we need to add a check if TOEI counter is v0. We can simply set v02 to 0. Otherwise, let's test it now. Enter a few numbers, then AV letter Q. You should see the correct average printed. Now try running it again and entering YD immediately. It should still print the correct average, 0 in this case. To make a wedding invitation feel more personal and sincere, The simplest trick is to include the guest's name in the message. This way, every guest feels like the invitation was written just for them. Of course, if you're sending invitations to many people, manually changing each name would be a huge hassle. But for those of us who can write code, this is not a problem at all. Let's say we have a wedding invitation template with several places where the guest's name needs to be inserted. With a contact list, we can use a for loop to insert each name into the correct positions. Since the line of code is quite long, we can use a backslash to break it into multiple lines. Assuming we already have a function called sendIMessage that sends messages based on the contact's name, this program can now automatically generate the invitation text and send it to each guest. Next, let's level up the scenario a bit. Suppose we not only want to replace the guest's name automatically, but also insert the wedding date. This way, by changing just the date, the same invitation template can be reused over and over again. However, if we keep using string concatenation, the invitation text will be chopped up by lots of plus signs, making it hard to read and painful to maintain. Python provides two cleaner and more elegant ways to format strings. The first one is the format method, which lets us write message content like this. Curly braces mark the parts to be replaced, and the numbers indicate which arguments from format will be used. Here, 0 refers to the first argument, name, and 1 refers to the second argument, wedding date. When name is Alice and wedding date is the 20th of May 2050, message content will look like this. Now the entire message is contained in one complete string, which is much easier to read. With format, you can also replace values by keyword instead of by position. In this case, the positions of the name and date don't matter anymore. Only the keywords do. For example, if the keyword receiver name is assigned the value name, every occurrence of receiver name will be replaced with the value of the name variable. For an even cleaner approach, you can reuse the variable names directly in the string, as long as you remember that the part before the equal sign is the keyword, and the part after it is the value. Besides using format, you can also use f strings. By adding an f before the string, the expressions inside the curly braces are evaluated directly and inserted into the string. For example, if year is the 20th of May 2050 and name is Alice, this will produce exactly the result we want. In addition to formatting strings, numbers can also be formatted inside strings. For instance, if we have a dictionary of student names and their GPAs, even though GPA is a floating point number, format can print it without manually converting it to a string. You can also use a colon, dot, number, and f to control how many decimal places a floating point number keeps. For example, adding 2f will format the GPA to 2 decimal places. The same applies to f strings. Adding 2f inside the braces keeps all GPAs at 2 decimal places. Suppose we want to write a program that calculates the area of a circular sector and prints it out. The formula for the area of a sector is the central angle divided by 360, multiplied by pi, and then multiplied by the square of the radius. If we approximate pi as 3.14, and the central angle is 160 degrees with a radius of 30, the program would be written like this. If our program needs to calculate the areas of different sectors in multiple places, we'll end up with a lot of very similar code, where the only differences are the angle and the radius used in the formula. In software development, there is a principle called the dry principle, don't repeat yourself, which means you shouldn't copy and paste the same code over and over again. These chunks of duplicated code clearly violate the dry principle. Functions can help us avoid this kind of repetitive coding. We've actually encountered functions very early on, such as print, sum, and type. These are built-in functions in Python. Each function is responsible for performing a specific task. When using a function, we call it by writing the function name followed by parentheses, with the arguments we want to pass in placed inside the parentheses. But we can not only call functions, we can also define our own functions. You can think of defining a function as building a machine that handles a specific task. Once the machine is built, whenever you need that task done again, you just use the function instead of redefining it every time. For example, let's first try defining a function that calculates the area of the first sector. First comes the def keyword, which indicates that we are defining a function, followed by the function name, parentheses, and a colon. Then we use indentation to indicate which lines of code belong to the function definition. Next, we can move all the code that calculates the area of the first sector into this function definition. At this point, the function has been fully defined. It's important to note that when a function is defined, none of the code inside it is executed. The code only runs when the function is actually called. Now, whenever we want to print the area of the first sector, we only need a single line of code, the function name followed by parentheses, to call calculate, sector 1. Python will then execute the code inside the function line by line and print the area of the first sector. However, this function still has a problem. While it works well for repeatedly printing the area of the first sector, what if we want to print the area of a second sector? Do we need to define another function called calculate size sector too? That would still introduce similar duplicated code. We can make this function more general by using parameters. This is like having a machine that makes buns. At first, you only want pork buns with white dough, so whenever you press the button, the machine gives you a pork bun with a white wrapper. Later, you realize you also want chive buns with purple dough or beef buns with green dough, so you switch to a more general machine one that takes the filling and the dough as inputs. If you give it beef, it makes a beef bun. If you give it purple dough, the wrapper comes out purple. This is much more flexible than a machine that can only make pork buns with white dough. Back to our sector calculation function. The first step is to remove the 1 from the variable names. Since this function is no longer limited to just the first sector, then inside the parentheses, we add 2 parameters, the central angle and the radius. Once we have these parameters, we no longer need to assign values to those variables inside the function. This is because when we call the function, these parameters behave like variables and are assigned the values we pass in. Now we have a function that can calculate and print the area of a sector for any central angle and any radius. After defining our own function, all those large chunks of code can be compressed into something simple and elegant. But this function can still be improved even further. We'll talk about that next time. In the previous video, we defined a function that can calculate and print the area of a sector for any central angle and radius. We compressed the code into a much simpler form and said goodbye to copy and paste coding. However, this function still has a problem. In the original program, sector area 1, sector area 2, and sector area 3 were assigned the areas of the first, second, and third sectors. Whenever we needed these results later, we could reuse them directly. But in our new version of the program, we don't have any variables storing these calculated results, so we can't use them afterward. You might be wondering, isn't sector area already assigned the calculated result? To understand this, we need to talk about scope. Variables defined inside a function are local variables and cannot be accessed outside the function. For example, if we define a variable a with a value of 3 inside a function, we can access it normally within that function. But outside the function, whether before or after calling it, Python will say that a does not exist, because it only exists within the function's local scope. Therefore, running code by calling a function is not exactly the same as running that code directly. From this perspective, although functions help us avoid repetitive code, not being able to access internal variables might seem limiting. That's where the return statement comes in. A return statement specifies what value a function should give back after it finishes executing. This return value can be assigned to a variable, printed, or used in any other way. Most importantly, it allows us to keep using the value outside the function. If a function doesn't have a return statement, Python returns none by default. That's why functions like print and append are usually called directly, while functions like len and sum are often assigned to variables. Our current sector area function only prints the result, it doesn't return it. Using the bun-making machine analogy again, it's like the machine makes a bun and only tells you what it made, but never hands it back. Once we add a return statement, we can store the result in a variable and use it for further operations. Now it's time to put this into practice. We previously wrote a BMI calculation formula, body mass index equals weight divided by height squared, this time. Our goal is to rewrite this calculator as a function. It needs to meet the following requirements. First, it should be able to calculate the BMI for any given weight and height. Second, during the function's execution, it should print a line your BMI category is, followed by the category name, such as underweight, normal, overweight, and so on. Third, it must return the calculated BMI value. You can pause the video now and try to write it yourself based on this information. Okay, I'll start. To define a function, valphi, followed by the function name, parentheses, and a colon. Since this function calculates BMI for any weight and height, both weight and height need to be included as parameters. The BMI formula is very simple and straightforward. Weight divided by height squared. Next, we need to determine the BMI category. If BMI is less than or equal to 18.5, the category is underweight. If it is greater than 18.5, but less than or equal to 25, we can simply write this condition as Gutty BMI equals 25. This works because the case for less than or equal to 18.5 is already covered in the first branch. So, when we reach the second branch, BMI is already guaranteed to be greater than 18.5. Following the same logic for the next one, if BMI equals 30, the category is overweight. Finally, if it is greater than 30, that is obese. We can use 会计 elsewhere for this and set TOA category equals obese. Then we need to print it. The printed line is your BMI category is. We can use an F string here, placing the variable inside curly braces. Most importantly, we also need to return the calculation result. We turn BMI now the function is ready. Let's test it by calling the function. For example, with 1.8 and 70. We can see it prints the BMI category. If we want to see the actual BMI calculation result, we can assign the function's return value to a variable and then print it. We can see the calculated result is also successfully printed. There's a popular saying among programmers, don't reinvent the wheel. It means that since round wheels have already been proven to work well, you should just use them instead of trying to invent a new wheel with a different shape. Of course, this idea doesn't work when you're in school. You can't tell your teacher, the class representative already got full marks, so I'll just copy their homework. No need to reinvent the wheel. But when writing code, directly using code that others have already written is perfectly normal and very efficient. For example, suppose you want to calculate the sum of all the numbers in a list. You could write your own function and call it every time you need to calculate a sum, but Python already provides a built-in function called sum. You can call it directly to get the total of all the numbers in a list, so there's no need to define your own. You can check the official Python documentation to see all the built-in functions, including ones we're already familiar with, such as print and len. However, the number of built-in functions is limited, and in many cases, they're not enough to solve our problems. For example, there isn't a built-in function that helps us calculate the median. At this point, we can turn our attention to other modules in the Python standard library. Our module is essentially a Python program. After you import a module, all the functions and variables inside it become available for you to use. For example, if you want to calculate the median of a list of numbers, you could write your own function. First sort the list, then use indexing to get the middle value. Here, the two slashes together mean integer division. After dividing, the result is rounded down. But instead of defining everything yourself, you can also use functions from Python modules. For example, Python has a module called statistics for statistical calculations, and it includes a function called median that computes the median. As a result, this whole chunk of code can be simplified into just two lines. The first line imports the statistics module, and the second line uses the median function from that module. Some people might wonder why sum is a built-in function, but median isn't and has to be imported first. The reason is that built-in functions are extremely common, while median is not used as frequently. It's like everyday furniture, such as a television, which you keep right in your living room. Less frequently used items like a barbecue grill can be stored away and taken out only when needed. There are 3 ways to import modules. The first way is using the import statement, which we've already seen before. After import, you write the module name. For example, import statistics. When you want to use a function or variable from that module, you use module name. Function, name or module name. Variable, name. The second way is using the from, import statement. After from, you write the module name, and after import, you list the functions or variables you want to use, separated by commas if there are multiple. The advantage of this approach is that you don't need to prefix the module name every time you use those functions or variables. The third way is using from import asterisk, followed by the module name. This imports everything from the module, so you don't need to prefix the module name when using any of its contents. Although this can be convenient when you need many things from the same module, it's still not recommended. The reason is that using asterisk imports all functions and variables, including many that you may never use. If you import both module A and module B, and they each have a function called ABC, you'll run into a naming conflict. When you call ABC, it becomes unclear whether you're calling the one from module A or module B. But if you use the first import method, the module name makes it very clear which module the function comes from. And if you use the second method, you can selectively import only the ABC function from module B. In the official Python documentation, you can find all the modules in the Python standard library. These include modules for working with strings, dates and times, files, regular expressions, mathematics, and more. Clicking into a module shows detailed descriptions of the functions and variables it contains. If you're curious about how a function is actually implemented, you can look at the source code written by others. In PyCharm on Windows, you can hold down the Control key and click on the function name. On MacOS, you hold down the Command key and click on the function name. But sometimes, even the modules in the Python standard library are not enough for our need. In addition to official modules, we can also import modules from third-party libraries. Third-party libraries are not provided by Python itself. They're created by other developers, so they are far more numerous and diverse. The syntax for importing third-party modules is exactly the same, but the difference is that you need to install them first, which means downloading them from the internet. As an analogy, installing a library is like moving a piece of furniture from the store into your warehouse, while importing it is like taking that furniture out of the warehouse to use it. All modules in the Python standard library are already in the warehouse, so you only need to import them. Third-party libraries, however, exist only on the internet, so you need to install them first, and then import them when you want to use them. The website pypy.org lets you search for third-party libraries. For example, you can find a financial data library called Akshar there and read about its features and usage. To install a library, go to the terminal and type pip install followed by the library name. For example, pip install Akshar. After installation is complete, you can import it using import. Once imported, you can use the functions in that module. For example, you can use the get safefaxadaily function to retrieve trading data from the China Financial Futures exchange for the 22nd of February 2022. Python has many interesting third-party libraries. Feel free to explore them. For beginners learning programming, one unavoidable hurdle is object-oriented programming, also known as OOP. Of course, it doesn't mean sitting your significant other across from you and writing code together, but fully understanding OP can be just as hard as finding a partner in the first place. Friendly reminder, this video is meant to help you understand the concept of OOP. We won't go into detailed OOP syntax here. Python is used only for simple demonstrations. Syntax details will be covered in a later video. Object-oriented programming is usually discussed in contrast with procedural programming. Before learning about objects, most of what we do is procedural programming. Procedure is code that performs a specific task, which you can basically think of as a function. The core idea of procedural programming is to break a task into steps and execute them one by one. For For example, if we write an ATM program that deposits 50 units of money, and then withdraws 100, we simply write these steps in order and define deposit and withdraw functions. If we also need to record which ATM performed the transaction, which bank it belongs to, and the serial number of the banknotes, we can add all of these as function parameters. There is nothing inherently wrong with this approach, but if we need to track even more properties, like the ATM branch or the year a banknote was issued, the number of parameters quickly grows. On top of that, both ATMs and banknotes have IDs, and mixing these values together as parameters makes it harder to understand what each piece of data actually represents. As the program grows longer and more complex, the clarity of the code can suffer. But what if we use object-oriented programming instead? As the name suggests, instead of focusing on procedures, it centers around objects. In OOP, we don't start by asking whether the first step is depositing or withdrawing money. Instead, we model the real world and think about what objects exist, what properties they have, and what actions they can perform. For example, every ATM has its own properties, such as an ID, a bank, and a branch. We can extract these properties, define an ATM class, and then create objects from that class. The relationship between a class and an object is that a class is a template, and an object is an instance created from that class. More intuitively, you can think of a class as a blueprint used to build objects. The blueprint specifies that an ATM has properties like ID, bank, and branch. So whether it's ATM1 from a bank, S branch with ID 001, or ATM2 from B bank, N branch with ID 002, they are all ATM objects. Their IDs, banks, and branches are simply the attributes of each individual ATM object. In the same way, we can define a banknote class and create banknote objects from it. Now, these objects can be passed directly as parameters to the deposit and withdraw functions. You might say, hold on, there are fewer parameters now, but we've added a lot of code to define classes. Isn't that a bad trade-off, beyond reducing parameters? OP groups related properties together, which helps make program logic clearer. For example, although both ATMs and banknotes have IDs, using ATM1 ID versus banknote 1, ID makes it very clear which object the property belongs to. And if we need to print transaction logs, without objects we'd have to pass a large number of parameters around. With objects, we can directly access the attributes bound to them. Compared to passing around lots of raw data, this makes both the logic and data flow much clearer. Besides attributes, another thing that can be bound to an object is methods. Just like in the real world, objects have properties and can perform actions. Attributes represent what an object has, while methods represent what it can do. Let's again use procedural programming as a familiar example. To wash clothes, we write out the steps in order and define functions like loading, starting the machine, washing, and drying. Procedural programming is like an instruction manual that guides each step one by one. What about object-oriented programming? Here, both the person and the washing machine are objects involved in the task. The person can load clothes and start the machine, and the washing machine can wash and dry. These actions can be defined as methods in their respective classes. From another perspective, a method is simply a function defined inside a class, and an attribute is just a variable defined inside a class. After defining the classes, we can create objects from them and let each object execute its methods. Compared to procedural programming, which focuses directly on execution steps, OP first assigns responsibilities to objects and then describes how those objects interact. As one popular analogy puts it, procedural programming is like a chronological record, while object-oriented programming is like a set of biographies. Objects not only bundle related attributes and methods together, but also help handle complex logic more elegantly. For example, if a washing machine method needs to know the machine's capacity, capacity can be set as an attribute when the object is created. Any method that needs this information can access it directly as an attribute, without requiring it to be passed in as a parameter. From these examples, we can see that when logic or information becomes complex, OP helps keep things clearer and more organized. In addition to these benefits, OP has 3 frequently mentioned features: encapsulation, inheritance, and polymorphism. Even though these words are familiar individually, their meanings aren't very intuitive when put together. But don't worry, we'll go through them one by one. Encapsulation means that the person who writes the class hides its internal implementation details, and users of the class interact with it only through its public interface. You can roughly think of an interface as the set of methods provided for use. For example, if someone has already written a washing machine class, you only need to know what methods it has, what they do, and how to use them. You don't need to know how those methods are implemented internally. This mirrors the real world. When we use a washing machine, we just press buttons on the control panel. We don't need to understand how it works internally or examine its circuitry. Encapsulation reduces the mental effort spent on unnecessary details. Inheritance means that OP allows classes to be organized into hierarchies. Just like in real life, where a son inherits from his father and the father from his grandfather, classes can have parent and child relationships. For example, both elementary school students and college students are students. They have student IDs, grades, and go to school. These shared characteristics would lead to a lot of duplicated code if handled separately. We can create a parent class called student, and let elementary student and college student inherit from it. This allows child classes to inherit attributes and methods from the parent class, reducing redundancy. Polymorphism means that the same interface can behave differently, depending on the object's actual class. For example, although both elementary students and college students do homework, the difficulty level is clearly different. So the homework method shouldn't be defined directly in the parent class, but instead implemented separately in each subclass. Imagine you're a parent with one college student and one elementary school student. When you tell both of them to do their homework, you don't need to worry about the difficulty. You just call the same homework method. Because they belong to different classes, each will execute a different version of the method. This is polymorphism. Without classes, you'd have to use if statements to check which type of child it is and manually call different functions. Polymorphism in OP lets you call the same method name without needing explicit type checks. That said, this doesn't mean OP is always better than procedural programming. If UPROP completely outperformed procedural programming in every way, procedural programming wouldn't still be widely used. Ultimately, the choice depends on the specific scenario and requirements. Oh, of course, if you're using a purely procedural language like C or a purely object-oriented language like Java, the choice is already made for you. By now, you should have a deeper understanding of this not-so-easy concept of object-oriented programming. If it still doesn't fully click, just save the video and watch it a few more times. It will eventually make sense. After watching the previous 8-minute video on understanding object-oriented programming, you should now have a general understanding of classes and objects. A class is a template used to create objects, and an object is an instance of a class. A class defines what attributes and methods an object can have, while different objects can have different specific attribute values. In this video, we'll dive into the actual syntax of object-oriented programming and create our own class. First, we use the keyword class, followed by a space, and the class name. Unlike variable names, which typically use snake case, Python class names use Pascal case, where each word starts with a capital letter. After the class name, we add a colon to indicate that the code below belongs to the class definition. As an example, we can define a cuteCat class called cuteCat. The next step is to think about what attributes objects of this class should have. A cat can have attributes such as name, age, and code color. A class has a special method called the constructor, whose main purpose is to define the attributes of an instance. It must be named self-init with 2 underscores before and after the name. The parentheses can contain any number of parameters, but the first parameter is always reserved to represent the object itself. And by convention, it is called self. It allows you to bind attribute values to the instance object. For example, if the cat's name is Lambton, you can write self, name equals Lambton, which assigns the value to the object's name attribute. If you write name equals Lambton without self, Python treats it as a normal variable assignment and does not consider it an attribute of the object. Now we can create a cat object in Python. We create an object by using the class name followed by parentheses with arguments inside. This calls the forInitTool method and returns an object. You might wonder, Wait a second, ini2 still needs the self parameter. Where did it go? You don't need to pass self manually. Just remember that Python handles it for you. When you call Qtcat to create an object, the ini2 method runs automatically, assigns the name attribute, and the cat object named Lambton is created. To access an object's attribute, use the object name followed by a dot and the attribute name. For example, cat1. Name returns the value of the name attribute bound to the cat1 object, which is Lambton. Of course, not all cats are named Lambton, so we should make Suiniti more flexible by assigning attributes based on parameters. When creating an object, we then pass the cat's name as an argument in the parentheses. The inito method runs, and the value of the name attribute is bound to the value of the cat name parameter. As a result, the cat object's name will be the value we passed in. We can also add more attributes to the cat, such as age and coat color, by passing the corresponding parameters when creating the object. All of the object's attribute values will be bound to the values passed in through the parameters. You've now learned how to define attributes and create objects, which is a big step forward in object-oriented programming. But classes can do more than define attributes. What an object has, they can also define methods, which describe what an object can do. To find out what comes next, stay tuned for the next video. In the previous video, we created a cute cat class and defined that objects of this class can have attributes like name, age, and color pattern. Let's review. Using the class keyword, we can create a class. Using the for ini2 constructor method, we can define what attributes an object will have. By writing the class name followed by parentheses, we can call fundiniti to create a new object and assign values to its corresponding attributes. But there's one thing we haven't covered yet, defining the methods that an object can have. Methods represent what an object can do. For example, a cute cat object can think and meow. Defining a method is straightforward and similar to creating a regular function, with two key differences. First, it must be written inside the class, indented to indicate that it belongs to the class. Second, like for init, the first parameter is reserved to represent the object itself, conventionally named self. Init, we said self allows us to bind attribute values to the object itself. So why do methods also need this self? One reason is that it enables us to access or modify the attributes bound to the object within the method. For example, if the number of times a kitten meows is proportional to its age, we could write it like this. A string multiplied by a number repeats the string that many times. Meow multiplied by the object's age attribute means if the kitten is 1 year old, it will print meow. If it's 3 years old, it will print meow meow meow. This way, the result of the method call changes based on the object's attributes. To call a class method, use the object, followed by a dot, the method name, and parentheses with any parameters. Just like the constructor, we don't need to manually pass self. Methods can also accept more parameters. For example, a kitten can think, and the content of its thoughts can be passed as a parameter. When calling the method, simply put the parameter value inside the parentheses. And now it's practice time. Our goal is to define a student class whose attributes include the student's name, student ID, and grades in 3 subjects: physics, math, and biology. Additionally, it should be able to set grades and print all grades for that student. You can pause and think about how to write such a class. First, to create a class, use the keyword fundClass followed by the class name, setStudent, then define the fundinit method. Note the double underscores. As you can see, the editor has automatically added the first parameter, phi-cell4. Since each student's name and ID are different, we can pass them as parameters and bind them to the student object. Here, even though both are called phinamai, self name refers to the attribute bound to the object, while phiname is just a regular variable whose value is passed in as a parameter. Next, similarly, define the student's ID. For the 3 subject grades, we can define a dictionary, initially setting each student's grade for each subject to 0. If every object has the same initial value, we don't need to pass it as a parameter and can define it directly. Now, let's try creating 2 student objects. For example, create Foimite with a random ID. and then create memory. Now, if we use sym_by_object attribute name, we can access their respective attribute values. Let's run it and see. As you can see, their individual name attributes and grades attributes are printed. Next, we need to define a method to set grades and change these initial 0 values. Use the divide keyword followed by the method name. The first parameter in parentheses is still diselfie by default. Since we want to change the grade for a subject, we need to know which subject to change and what the new grade should be. These can be passed as parameters. There's an additional logic. We only change the grade if the subject exists. Otherwise, we do nothing. So we first need to check if the subject exists. If the subject is a key in the file self, grades dictionary, we update its corresponding value to the new grade. If key in dict can check whether the key exists in the dictionary. If it exists, update the value corresponding to the 40 key in the dictionary to the past don't-degraded parameter. Now, this method is complete. Let's test it by changing Mary's math grade to 95. Now, print it and see. As you can see, the grade for math is no longer 0. Next, write a method to print all the students' grades. Use the divide keyword again and name it to print 2 grades. This method doesn't need any parameters because the students' grades can be directly obtained from 7 self. Grade. For clarity, we can first print the students' relevant information, such as their name and ID. Then, to print all grades, we can use a for loop. The for loop can be written like this. Iterate over each one course, key in the for self grades dictionary. Then print the corresponding subject and its grade. We retrieve the score from the dictionary using the course key as the value. Now, this method is also complete. Here, course corresponds to subjects like physics, math, and biology, and this part corresponds to the numeric grades. Now, let's test it. For example, change Henry's physics grade and math grade, then call superint2 grades to print all their grades. As you can see, all the newly set grades are displayed. In the object-oriented world, if we abstract humans and kittens into classes, it would look like this. Humans have attributes such as name and gender, 2 eyes and no tail. They can also perform actions like breathing, using the bathroom, and reading. Cats also have a name and gender, 2 eyes and a tail. They can breathe and use the bathroom as well. Although they can't read, they can scratch your sofa while you're reading. Whenever we notice that we're writing repetitive code, we should recall an important principle in software development called DRY, which stands for Don't Repeat Yourself. Since we aim to minimize code duplication, there must be a better way to rewrite the code above. Only important feature of object-oriented programming is inheritance. It allows us to create hierarchical classes. Just like in real life, where a son inherits from his father, and a father inherits from his grandfather, classes can have parent and child relationships. Just like in genetics, where a baby dragon grows, whiskers like its parent, or a baby mouse knows how to dig holes, a child class inherits the attributes and methods of its parent class. Let's go back to our earlier class example. Humans and cats are both mammals. They both have 2 eyes and can breathe and use the bathroom. So we can create a class called mammal and move all these shared attributes and methods into it. Then both the human and cat classes can inherit from this class. The syntax is to add parentheses after the class name and put the parent class name inside. At this point, the constructor and the 2 methods, using the bathroom and breathing, are inherited even though they are not defined directly in the human or cat classes. Now, if we create a cat instance and the subclass does not define its own constructor, the parent class's constructor will be called, giving the instance attributes like name, gender, and number of eyes. When this instance calls the bathroom method, it will also use the method defined in the parent class. However, if the subclass defines its own version of that method, the subclass's method will be used instead. The logic here is that Python first checks the class itself for the method, and if it's not found, it looks up the same method in the parent class. However, we still haven't fully achieved what we want because humans and cats have different values for the has-a-tail attribute, so it can be defined only in the parent class. But if we define an init method in the subclass like this, the subclass constructor will be called first. and the instance will end up with only the hasTail attribute. All-in solution is to rewrite all the attributes, such as name and gender, inside the subclasses divinity, but that leads to duplicated code again. A more elegant solution is to use the super function inside the subclass. Super returns the parent class of the current class, so calling super. Init, inside the subclass's constructor, will invoke the parent's constructor. This gives the subclass instance attributes like name, gender, and number of eyes. Through inheritance, we successfully remove duplicated attribute and method definitions while keeping object creation, attribute access, and method calls exactly the same as before. Finally, here's a small tip. When should you use inheritance? If you can describe the relationship between two things as A is a B, then a can usually be written as a subclass of B. For example, humans are animals, so humans can be written as a subclass of animals. Electric vehicles are vehicles, so they can be written as a subclass of vehicles. Did you get it? Or are you completely lost already? Now it's time to practice. If you were to create a human resources system, for a company, employees are divided into two categories. Full-time and part-time, all employees have the attributes of name and employee ID, and there is a method to print information that can print out these two attributes. The difference between full-time and part-time employees is that full-time employees are paid monthly with a monthly salary attribute, while part-time employees are paid daily with a daily wage and an attribute for how many days they work. Per month, this difference leads to variations in how their monthly salary is calculated. Now you can pause and try writing a hint. You can use class inheritance, place the common attributes and methods of full-time and part-time employees into a parent employee class. Let me start writing now. First, define the parent class employee, then put common attributes like name and employee, ID all into the constructor. Then define a method to print information, to print out the name and ID. Next is the full-time employee class. Since full-time employees inherit from the employee class, add parentheses after the class name and write employee inside. Then comes the constructor, the initialization method for name and employee. ID is already written in the parent class, but we still lack the monthly salary attribute. So here, use super to refer to the parent class followed by init. This way, we can call the parent class's constructor, pass in the name and ID. Then also add the full-time employee's own monthly salary attribute. Finally, we need to calculate the full-time employee's monthly salary. This is quite simple. It is directly the employee's monthly salary. Then comes the part-time employee class. Similar to before, also inherits from the parent employee class. In the constructor, still use super. Init to initialize the name and ID part-time. Employees have two of their own attributes, daily wage and the number of workdays per month, so add these to the constructor as well. Finally, to calculate the part-time employee's monthly salary. This is a bit more complex than for full-time employees. It equals the daily wage multiplied by the number of workdays per month. Now the classes are defined. We can test with two employees. Create a full-time employee. Assign him a name, Idaho, and a monthly salary attribute. Then create a part-time employee. Similarly, assign him a name, Idaho, his daily wage, and the number of workdays per month attribute. Let's print their information, run it. You can see here, both are calling the print_info method inherited from the parent class. If we print their monthly salaries and run it again now, what is being called are their respective methods for calculating monthly salary. In programming, working with files including reading from and writing to files is very common. Documents, images, music, and other resources may differ in format, but fundamentally, they are all files. Files always belong to a directory. You can think of a directory as a folder. If we want to modify a text file, we usually go to the directory where it's stored, open the file, and edit it directly. But if we want to manipulate that file using code, a question arises: how does the program know where to find the file? To answer that, we first need to understand how directory structures work in operating systems. On Unix-like operating systems such as Linux and macOS, the directory structure looks like a tree with a root node called the root directory, usually represented by a /style files, and directories are stored under this root directory. Windows works differently. Each disk partition has its own root directory, represented by the drive letter followed by a \. Although these directory structures look different, file locations can be specified in two common ways: absolute paths and relative paths. An absolute path is a path that starts from the root directory. On Linux and macOS, absolute paths start with a /. Each directory in the path is separated by a /, and the path ends with the target file or directory. On Windows, an absolute path starts with a drive letter and a \. Directories are separated by backslashes, and the path also ends with a target file or directory. Our relative path, on the other hand, starts from a reference location and describes where another file is relative to that location. When using relative paths, a single dot represents the current directory, two dots represent the parent directory. To move up multiple levels, you can chain two dots together using slashes or backslashes, depending on the operating system. To move down into subdirectories, directory names are also separated by slashes or backslashes. As you can see, relative paths usually start with single dot or two dots. In addition, the dot and slash can be omitted, so if two files are in the same directory, you can refer to one another simply by using the file name. Many code editors can help you copy a file's path. For example, in PyCharm, you can right-click a file and choose Copy Path reference to get its absolute path, as well as its relative path based on the project root. Once we know how to locate a file using either an absolute or relative path, we can start working with it in code. We'll cover the specific file operations in the next video. If you need a program to help calculate sales data, one approach is to manually copy each data entry from the data file into the code, and then run the program to get the result. If you have multiple market data files from different dates, you would have to keep modifying variables in the program, which quickly becomes inconvenient. But once you learn how to work with files, the same piece of code can read different market data files, just by changing the file name, which is much more elegant. The first step in reading a file with Python is to open the target file. We use the open function and pass in the file path, which can be either a relative path or an absolute path. If you're not familiar with path, you can review the previous video. The second parameter is the mode, which is a string. Common modes include R for reading and W for writing. Since this video focuses on reading files, we use R. This parameter is optional if omitted. The default mode is reading. In read mode, if the program cannot find the file you specified, it will raise a file not found error, indicating that the file does not exist. The open function also has an optional parameter called encoding, which specifies the character encoding. Nowadays, most files use UTF-8 encoding, so passing UTF-8 will read the file using that encoding. If open executes successfully, it returns a file object, which can then be used for reading or writing operations. For reading files, the file object provides a read method. When called, it reads the entire file at once and returns the contents as a string. In general, the file formats we work with in code are usually simple and straightforward. For example, plain text files like txt are ideal because their contents can be easily converted into strings. Formats like Word files include fonts, colors, and styling, which often cause problems when reading them with code. Another thing to note is that if you call read a second time, it will return an empty string, because the program keeps track of the current read position in the file. The first call reads the file to the end, so there's nothing left to read on the second call. For very large files, it's best not to use read, because loading the entire file into memory can consume a lot of memory or even cause memory issues. If you don't want to read the entire file at once, you can pass a number to read, specifying how many bytes to read. The next call to read will continue reading from where it left off. Besides read, we can also use the readLine method to read files. This method reads only one line at a time, and each subsequent call reads the next line. It determines the end of a line based on newline characters, and the new line itself is included in the returned content. You might wonder, if a file has many lines, how do we know how many times to call readLine to reach the end? When readLine reaches the end of the file, it behaves like read and returns an empty string. That's why we usually use a while loop. As long as the returned string is not empty, we keep reading, otherwise we exit the loop. If reading line by line feels tedious, there's another method called readlines, which simply adds an S to the name. Readlines reads the entire file and returns a list of strings, with each element representing one line. It's commonly used together with a for loop. You read all lines first, then iterate over them one by one. At this point, we've learned 3 ways to read files, and you can choose the most appropriate one depending on the situation. After finishing reading a file, there's one more important step: closing the file. File objects have a close method. As the opposite of open, calling it releases system resources, so files should always be closed after reading or writing. Sometimes we might forget to call close. An alternative approach is to use the with keyword. With with, you call open, use as to name the file object, and place file operations inside the indented block. Once the block finishes executing, the file is automatically closed. This approach makes the code cleaner and eliminates the need to call close explicitly. Now it's time for practice. Since we want to practice reading files, let's first create a file to read. As mentioned earlier, code is best suited for reading plain text. To create plain text, you can use Notepad on Windows or TextEdit on MacOS. But an even simpler way is to right-click in the code editor, select New File, enter a file name, and use the txt suffix here to indicate it is a plain text file. Then write a few lines of content here. I'll just copy a random poem. Note that the file's location determines the path we need to input when reading the file. This file is currently created under my project folder. Now, back to our Python program. Before reading a file, we need to open it, so use the filepan function. This function is built into Python, so no import is needed. The first parameter is the file path. For simplicity, we can use a relative path. A relative path is relative to the current code file I am editing, where the file we want to read is located in relation to it, since the file to be read and the code file are in the same folder. The relative path is quite simple. It uses a dot to represent the current folder, followed by a separator. Note that on Unix-like systems, the separator is a /@, while Windows uses a backslash after the separator, add the file name. This indicates that the file to be read and the code file are in the same folder. The second parameter is the mode. Since we are reading the file, the mode is file. But this can be omitted because the default is FineWire anyway. We can also add the optional FineEncoding1 parameter. The default FineEncoding1 in the function follows the system, so it is better to explicitly specify encoding -8. The FileWeapon function will then return a file object. Let's name it tofile stands for file. Once we have the file object, we can start reading the file. The most straightforward way is to use the file reading method. It returns all the content of the file as a string. So here, we can first store this content in a variable, then print it to C. Finally, remember to call cycloc to close the file and release resources. Now we can run it to see the result. As you can see, with just 4 lines of code, the entire file content is printed, matching its original content. Sometimes we might forget to call file close, so we can also use while with for to avoid needing to manually close it. So here it would be swift with open as FL. Remove the for and close line, and ensure all file reading operations are indented under it. Run it again, and you'll see the result is exactly the same as before. Besides while read, we can also use while readline to read line by line. For example, if we call file readline twice, it will read the first 2 lines of the file. Also, note that all operations on this file object must be indented under with wait. If the second line isn't indented and falls outside the with block, by the time it runs, the file object would already have been automatically closed, resulting in an error. Let's fix the indentation and run it again. Another thing you might wonder is why using var readline produces extra blank lines. The reason is that var readline reads the new line character at the end of each line as well, and the for print for by default adds a new line at the end. So the combination of two new line characters creates an extra blank line. The third reading method we'll learn is var readlines. Let's print it directly to C. You'll notice it returns a list where each element is the content of a line. Here, we can clearly see that the new line characters at the end of each line are also read in as part of the file. Typically, var readline C is used with a for loop. We can first assign the read content to a variable, then loop through this list. Use it to print each line's content. You'll see the effect is also to print all the content of the file. Suppose you are a teacher who wants to calculate an overall average score based on students' exam results. In the previous video, we learned how to read files. So if the scores are stored in a file, you already know how to read them. But if the calculated result is stored only in a program variable, do you really need to rerun the program every time you want to see it? That's not very elegant. Besides reading files, writing files is also a very common operation. By saving the program's output to a file, you don't need to rerun the program repeatedly, and you can easily share the results with others. Writing files is very similar to reading files. In both cases, you need to open the file and close it after the operation is finished. So we can still use the familiar with open as syntax, with the file path passed as the first argument. For the second argument, we pass in the mode. The write mode is represented by the string W, so we use W in read mode. When the second argument is R, the program will raise an error if the file cannot be found at the given path. In write mode, this problem does not exist. If the file does not exist, the program will automatically create a file with a given name. We can also pass the optional encoding parameter to ensure the file is written using UDF-8 encoding. Only important thing to note is that opening a file in W mode will clear its existing contents if the file already exists. So use W carefully. After thinking it through, we can start writing to the file. The variable name you choose after as refers to the file object returned by the open function. For writing files, the file object provides a write method. For example, after doing this, the file data. txt will contain the line hello. If we call write again and pass in uu, what will the file look like? It will look like this. That's right, write does not automatically add a new line. So if you want line breaks, you need to include new line characters yourself. You might be wondering, what if I don't want to clear the original content and only want to append new data? In that case, you shouldn't use W mode. Instead, use A, which stands for append rather than overwrite. So if a file already contains two lines of text, opening it in a mode and calling write twice will append hello and uu instead of replacing the original content. Just like log a mode will also create the file if it does not exist. Another important point is that in both W and a modes, you cannot read the original contents of the file. If you try to call read on the file object, the program will raise an error because reading is not supported. So what should we do? Should we open the file once in R mode to read and then again in W mode to write? That would be unnecessarily complicated. By adding a plus sign to R, forming R, we can enable both reading and writing. After opening the file this way, calling read and write will both work. After calling write, new content will be appended to the end of the file. Now it's time for practice. This practice consists of two small tasks. You can pause and try them yourself first. Now, let's begin. The first task is to write these 3 lines of poetry into a file named SciPoem. txt, when dealing with file operations, first consider which mode to use. Here, we are writing content into a brand new file, so we can use the hide mode mode. In double mode, even if the file doesn't exist, the program will create it for us. We'll use the familiar with open. Inside the parentheses, first pass the file path. I plan to create it in the same folder as the code file, so the relative path starts with ibendap, followed by the file name. Of course, if it's in the same folder, the thorvat can actually be omitted. Then, for the mode, pass thorvat. It's still best to pass the forward encoding parameter as well to ensure UTF-8 encoding. After forward, as our very reasonable variable name. I usually use sorbet for. Next, we can write these 3 lines of poetry. Here, it's quite flexible. I could call the fi-write method 3 times, like this. But as it stands, this isn't quite right yet, because according to the requirement, each line should end with a new line. So we need to manually add new line characters. Now, let's run it and see the result. You'll see that type poem. TXT has been automatically created, and its format meets our requirements. Besides this approach, another method is to combine all the content into one string. This way, you only need to call fi-write once. Like this, run it and check, the effect is the same. The second practice is to append 2 more lines to the end of the same file. Here, it's better to use the Foisia mode, because using Foisia mode would clear the content we previously wrote. So first copy the Foisia width open as FOI line, change the mode to Foisia moi, and then call the Foisia write method at the end, putting these 2 lines inside. Don't forget the new line characters. Before running, there's one more thing to do. In the previous content, we need to add an extra new line character. Otherwise, the 2 sections will stick together. Alright, run it and check the result. Done! Isn't it straightforward and simple? See you in the next video where we'll use fur bar mode to read it. Sometimes the code we write is buggy and can crash the program, meaning it causes an error. Other times, the code itself is correct, but external issues, such as invalid user input, can still cause the program to crash. Once an error occurs at a certain line, all subsequent code stops running, which is often not what we want. Therefore, we need to learn how to anticipate problems and catch exceptions before the program crashes, so we can handle errors in the way we want, before learning how to anticipate errors. Let's first understand how programs can crash, or in other words, what types of exceptions exist. Accessing a list with an index outside its valid range causes an index error. Dividing a number by 0 causes a 0 division error. Trying to open a file that does not exist causes a file not found error. Performing an invalid operation, such as multiplying 2 strings, causes a type error, and so on. There are many types of exceptions, far too many to list them all. The more mistakes your code has, the more familiar you'll become with different kinds of errors. In practice, we should use testing and other methods to find and fix all avoidable bugs. But what if an error cannot be avoided by us as programmers? For example, suppose we wrote a program to calculate BMI and ask the user to input their weight. If the user enters a line of Chinese poetry instead of a number, it can't be converted, and the program crashes before you even get a chance to respond. However, if we can catch that exception, the program won't crash. We can catch exceptions using the try except statement. After try, we place the code that might raise an error inside the indented block. Next, after except, we specify the type of error we want to catch, followed by a colon. For example, if floats receives a string that cannot be converted to a number, it raises a value error, which we can catch using except value error. Inside the indented block, we write the code that should run when that error occurs. In this example, we can print a message telling the user to enter a valid number. In this example, besides value error, a 0 division error may also occur if the user enters 0 for height. We can catch it in the same way by adding another except 0 division error, with its corresponding handling code. Sometimes we can't anticipate every possible type of error. If you want the program to avoid crashing no matter what error occurs, you can use a bare except to catch all exceptions. It's important to note that try except clauses are checked from top to bottom. Only an exception is caught by the first matching except block. The remaining ones are skipped. This works similarly to if and elif, only the first matching branch executes. Now you know how to make a program respond to errors instead of crashing outright. After except, we can also add 2 more clauses, else and finally. The else block runs when no exceptions occur in the try block. For example, if the user input is valid, we can simply print the calculated BMI value. The finally block contains code that will always be executed, regardless of whether an error occurs. The powerful part of finally is that it runs whether an error was caught, no error occurred, or even an uncaught error caused the program to crash. Are you completely confused yet? besides using exception handling to prevent crashes. Testing is also very important in everyday coding. How do we make sure our code is bug-free? Stay tuned. We'll cover that in the next video. One day in 1947, computer scientist Grace Hopper discovered that a machine malfunction was caused by a moth that had flown into a relay and been electrocuted, leading to a hardware failure. The word for insect in English is bug, so it later came to be used in computing to mean a program error. Just as no human is error-free, it's perfectly normal for programmers to write bugs. What matters more is how quickly we can find and fix bugs, instead of letting them reach production and having users discover them first. This is exactly why testing exists. Its purpose is to verify whether a program behaves as we expect. In addition to validating new code, testing also ensures that changes to existing code don't break parts that should remain unaffected. So how do we test when writing Python? Ta-da-da! Let's introduce the assert statement. Assert means to assert, and it can be followed by any Boolean expression, an expression that evaluates to true or false. When testing, we place an expression after assert that we believe should be true. If the expression evaluates to true, nothing happens and the program continues running. If it evaluates to false, an assertioner is raised, essentially saying, hey, this doesn't match expectations. One downside of assert is that once an assertioner occurs, the program stops immediately, so we can't see if other issues exist later in the code. That's why we usually use dedicated testing libraries. These libraries can run multiple test cases at once and clearly show which ones passed and which failed. Unitest is a commonly used Python unit testing library. Unit testing means testing the smallest testable units of software, such as verifying whether a function behaves as expected. The Unitest library comes built into Python, so no installation is needed, but we still need to import it. We usually place test code in separate files rather than mixing it with the implementation code. This helps keep implementation and testing responsibilities clearly separated. Suppose we previously wrote an addition function called myAdder in myCalculatorPy. We can write test cases for scenarios like positive plus positive or positive plus negative. To test the function, we also need to import it into the test file. If the test file is in the same directory, we can use from filename import function shname or classname. Now we're ready to write tests. Create a class, usually starting with test, and make it a subclass of Unitest. Test case to access testing features. Inside this class, each test case is defined as a method whose name must start with test_tort. This naming is crucial because Unitest automatically discovers methods that start with test before. Writing a test, think about the expected behavior of myAdder. For example, if we pass in 5 and 3, it should return 8. If we used assert, we might write it like this. But since assert stops execution on failure, we can instead use the assert_equal method from Unitest. Test case. Since our test class inherits from test case, we can call this method directly using self. If the two values are equal, the test passes. If not, it fails without crashing the program. After writing tests, we can run them by typing Python munitest, which automatically discovers and runs all testy methods in test case subclasses. It tells you how many tests were run, and those dots aren't silence. Each dot represents a past test. If a test fails, one of the dots becomes an funitest. Also provides detailed information about which file and method failed and why. Unitest also offers advanced features to help us test more efficiently and catch bugs. For more details and practice exercises. As mentioned earlier, Python's built-in Unitest library can automatically discover and run all test cases, display all test results at once, and provide detailed information for failed tests, greatly improving the efficiency of unit testing. In addition to the commonly used assert_equal, the test case class provides many other assertion methods. For example, assert_true works like assert_value is true, and asserting works like assert_item in container. These methods also have corresponding negated versions, such as assert_notequal, which is similar to assert_value1 equals value2, and assert_false, which checks that a value is false. In principle, assert_true can replace all of these methods. For example, both of these tests check whether 2 is not in the list, 1, 2, and they produce the same pass or fail result. However, it's still recommended to use more specific methods. For instance, if you want to test that an element is not in a list, use assert notin instead of the generic assert true. This is because more specific assertion methods provide clearer and more informative failure messages when a test fails. Sometimes, we can further improve testing efficiency by using additional techniques. For example, when testing a class, we need to create an instance in order to call its method. Since each test case is independent, we often need to create new objects repeatedly when testing different methods. To reduce unnecessary repetition, we can use the setup method provided by the test case class. Before each test method, those whose names start with the setup method is executed once. This way, we can create the test object once in setup, store it as an attribute of the test class, and then access it in each test method. Now it's time for practice. Suppose we have already written a shopping list class. It includes these methods. First, the constructor method, it assigns the shopping listy attribute to the passed-in dictionary. The dictionary contains item names and their corresponding prices, just like this example. Then, the getAppamCounter method returns how many items are in the shopping list. The getTotalPrices returns the total price of all items in the shopping list. To write a test program for this class, first create a new file. You can name it starting with soytest for example. For test shopping list, to use the unitest.b library to help us test. Write an import statement to include it, then also import the class. To be tested, from file name import class name. Now, we can officially start writing the tests. Create a new class. Make it inherit from the FoyTestCase class. In the FoyTestCase class, in the unitest.d library, we can first test the suiD key. NiTeamCount method, note that methods must start with suiTestD to be automatically recognized as test cases by unitest. Suppose we have a shopping list, like this. It contains these shoe paper 8, a hat 30, and slippers 15. If we call the FideSueGate item counter method of the shoe shopping list, it should return 3 to us because there are 3 items, so we can write shoyself as a tackle. Then the value returned by YGetTotalCounter equals 3 next. Test the the TotalPrice method. We can still use the same shopping list after calling the TotalPrice method. The correct value it returns to us should be equal to how much is it. It should be 53, so we still use the FidoUseDself as a tackle method, passing the number 53 as the second argument. But here you can see we are actually repeatedly creating this test object, so we can consider using the number 53 as a top FA. Method, note that its name should be exactly the same as here. Then inside, we can create an attribute, for example, called ForShoppingYlisty. This name can be chosen arbitrarily. The attribute name isn't important next. All places that use the specially created T shopping listy, we can modify them accordingly. Here there is an error. It says the variable folding listu does not exist. We need to use WeToonDself. Shopping when listy here. That is its attribute, this place, FuVinself. Shopping list, now we can run it. To see open the terminal, we enter the test command, which is Python munitest here. It says 2 test cases were run, and the test result is 2 dots indicating both test cases passed. If we intentionally change the number to a wrong one and run the same command again, then we can see one of the dots becomes an in. Which one did not pass? It shows us the method that failed the test. Then below, we can see it even points us to the line where the test failed. It also tells us the reason the test failed is that 53 does not equal 55. That is, the first argument, its value is 53, and the second is 55. They are not equal, so through unit testing we can confirm whether the program behaves as expected after making changes to the original code. We can also use unit testing to verify that the parts we don't want to be affected still execute as expected. Suppose we want to calculate the square of a number and print the result in a formatted way. We can write a function like this. It mainly does 2 things, calculation and printing. For example, when we pass in the number 3, the output will look like this. This is a very simple function, but what if we want to extend it? For example, to print not only squares, but also cubes. All-in possible solution is to pass in an extra parameter indicating the power, 2 for square, 3 for cube. Now another problem arises. What if we also want to print the result of adding 10 to the number? At this point, it may feel hard to proceed. No matter how you change the logic, it starts to look messy. From another perspective, the reason this feels awkward is that we've kept the calculation logic tightly coupled inside this function. But what if we pass the calculation itself as a parameter? In that case, we can first define separate functions for squaring, cubing, and adding 10. Inside the calculation and printing function, we simply call the passed-in function to get the result and then print it. What that function actually does, whether it calculates a square, a cube, or adds 10, is not the concern of this function. When calling it, if we want to calculate and print the square, we pass in the square function. If we want to calculate and print the result of adding 10, we pass in the corresponding function instead. Yes, functions can be passed into other functions. A function that takes another function as a parameter is called a higher-order function. One important thing to note is that when passing a function as a parameter, you pass the function name itself without parentheses or arguments. Once you add parentheses, the function gets executed, and what you pass in is its return value, not the function itself. After switching to a higher-order function, the overall logic looks like this. This approach is easy to extend. For example, if we often need to calculate and print the result of multiplying by 5, we can simply define another function and pass it in when needed. We can even pass a formatting function as a parameter, allowing us to support different output formats without changing the calculate t and $print function itself. In summary, higher-order functions provide much more flexibility in our programs. A real-world analogy would be a multi-purpose hairstyling device. The main unit handles airflow, temperature, and speed, while different attachments, like curling barrels or nozzles, enable different functions using the same base. The higher-order function is like the main unit, and the functions passed in as parameters are like the attachments. Sometimes, however, the function we pass into a higher-order function is only used once, and giving it a name and defining it separately can feel a bit excessive. Anonymous functions are well suited for situations like this. As the name suggests, anonymous functions don't require a name and are often used as one-off, disposable function. If we must refer to them by name, we usually call them lambdas, since they are defined using the lambda keyword. We can define a lambda function directly inside the call to a higher-order function, starting with a lambda keyword, followed by parameter names and a colon. The variables before the colon represent the parameters passed into the anonymous function. After the colon, we don't need to write return. We simply place the expression whose value will be returned. To add more parameters, we just list them after the lambda keyword, separated by commas. You can think of an anonymous function as a function without a name that takes up fewer lines of code. For example, if we rewrote this anonymous function as a regular function, it would look like this. As you can see, anonymous functions reduce the number of lines, avoid naming, and don't require indentation, making them ideal for one-time use cases. Besides being used as arguments to higher-order functions, anonymous functions can also be defined and called directly. Just like regular functions, the only difference is that the lambda expression itself must be wrapped in parentheses to be treated as a single unit. However, anonymous functions have limitations. They can only contain a single expression, so they are suitable only for simple cases. For complex, multi-step logic or scenarios involving loops or recursion, lambda functions are usually not flexible enough. Even if such logic can be written using a lambda, readability often suffers, so in those cases defining a regular function is the better choice. See you in the next video.